Could you send me a feedback? Could you hear?
Yes,
Yes, we
perfectly.
can.
Thank you very much. And thank you for participating to this afternoon session of our doctoral course on modeling in composites, multi-scale modeling in composites. And we have the pleasure and the honor to host in the presence Professor Adnan Ibrahimbegovic, that is a professor of class exceptionnel, member of the Università, France, and chair for computational mechanics at the University of Technology of Computation. I don't know if this is right.
Everything is fine. Everything is fine. Yes.
And he has obtained his engineering education in Sarajevo and PhD at the University of California, Berkeley, and habilitation at the University of Marie Curie, Paris, in France. And he is the past chairman of SS Kashan Teaching and LMT Kashan Research Departments and the head of master program MAISA. And maybe if you want to spend some words about your master program, you are welcome.
Sure.
And he has a great number of international awards, and including IACM Fellow Award, Humboldt Research Award for Germany, Research Award for Slovenia, International Fellowship for Canada, and many other international distinctions. And this afternoon we have the occasion to attend his lecture, and then we will ask you for intervention.
Excellent.
If possible. Thank you, and welcome.
Perfect. Just to prove that we are really in person, so everybody is there. Okay. Perfect, guys. Huh? Next time, I hope you'll be in person as well. Let me stop video. Maybe it will be less messages, and I'll try to share the screen and have the best possible image that we can afford. Let's try this one with the PowerPoint. Is that going to be up? And I'll do this one. Okay. So do you see my screen? Is that okay? Can you? Anybody answers? Can you answer?
Yes, Professor, we can see.
Excellent.
Yes, we can see your screen, Professor.
Okay, so I would like to start this presentation to first saying grazie or merci in these European languages, and then in this pidgin English that everybody speaks in scientific community, to Professor Patrizia Trovalucci of Sapienza, Roma. First, thank you for inviting me to this course, because she gave me good excuse to come to beautiful city of Rome. Second, I wanted to thank Patrizia for accepting to do a distinguished lecture on the conference I organized not such a long time ago in beautiful city of Split. And since, because the COVID did not really at that time cleared up, it was end of June, I believe July, there were not all the distinguished lecturers who came in person. Unfortunately, Patrizia was among those who didn't come to person. So for her, I put this picture. This is the city of Split. It is not as beautiful as Rome, so you don't have to regret that. But there's a famous Diocletian Palace, and it's the only monument that goes back to Roman times. Diocletian was one of the Roman emperors, less known than Julius Caesar, but he decided to retire. So if ever one day important professors like Patrizia Trovalucci decide to retire, you can come to Split and build a house like that, no problem there. So this is like a message. I'm really glad to be in also distinguished company of many of the professors who are going to be teaching. And I think that Patrizia did an excellent job by bringing many professors to expose their way of doing. Because when a younger person who is doing a PhD is supposed to do a studying, the best way to learn is to have several different versions of the same thing. Then the only hope you have is to build your own version, which is the goal of the PhD studies anyway. So let me just introduce, Patrizia already said many things that I did, but put in a nutshell, I had a good fortune to be winner of Fulbright scholarship for my home country that used to be former Yugoslavia. And then that allowed me to go and do my PhD studies in computational mechanics at Berkeley with people like Bob Taylor, like Zinkage Taylor, and Ed Wilson, another very famous guy who wrote SAP, first computer code, which had a worldwide reputation. Then I came to France, maybe not making the best choice to be a professor. It would have been better if I would stay in US or Germany, but young people make mistakes. So what the hell? There I had to do habilitation. I did that in the best French university called Pierre Marie Curie. So I became also full-size professor, and even the highest professor, this is what is called classe exceptionnelle. I became this rather early in 2009. It's been already more than 10 years. That means you have no more promotions. And then you can just go around. And basically, when I say go around, I typically try to find students from all over the world. And I do have students from different countries. Every country basically gave me an award. I had a student from that country, starting from whatever, the Brazil, from Turkey, Korea. Korea, I got a Vietnamese guy, very good one. She had to be best student for masters in program in Korea, Mexico, and so on and so forth. So basically, most of the stuff that I'm going to present is coming from the work that I was doing while being a professor at École Normale Supérieure Cachan. École Normale is one of these elite schools that go back to Napoleon Bonaparte, who created these schools to produce a French elite, basically. So Polytechnique was for officers. Now it's for managers. École des Mines was to get the mining out. Now it's also for managers. And the only one which really had the PhD candidates is École Normale Supérieure. These are professors for engineers. And basically, I was there in charge of many things for 15 years. And especially what I was in charge of was the collaboration with Électricité de France, which is the highest level French company which has a monopoly on producing electrical power. And the reason I left, first of all, is when they decided to move all these historical schools, which are in the city of Paris, to some remote location called Saclay, where there's nothing really. I said, my God, this is increasing my travel time to go back and forth. And secondly, I thought there was going to be lots of troubles before they organized such a big scale university. So I accepted offer from University Pierre Marie Curie, who got together with Sorbonne University, and they become now something called Sorbonne. So they are now world, whatever, high-ranking university, and they wanted this University of Technology, Technical University Compiègne, to become engineering college. So basically that means for me, I get the privilege to do only this research type of part of the work, do doctoral courses, teaching and things like that. And then year from that, I got another type of really very good arrangement. It's called Institut Université de France. This is a job for 40 professors who are given privilege of teaching very little. I just teach one doctoral course. And basically then after that, I can justify my professor job. And in exchange, I have to do many international projects with lots of people. So typically there's always lots of people who are doing a PhD with me. And I hope maybe some people from Italy. For some reason, up to now, I didn't have any people from Italy. It will come, hopefully. So this is the title of my lecture. I want to talk about multiscale modeling and computation of composite materials, and especially to have a really systematically two main messages. One is the size effect. What exactly size effect is? You interested in fracture failure of composite materials, you realize that if you break a small specimen, the dominant failure modes is not the same like breaking a very large specimen, even though these two materials are built of the same, these two structures are built of the same material. And basically, if you really want to be able to very quickly do some kind of decision-making process, then you have to go to so-called reduced modeling. Today, reduced modeling is a catchword in mathematics and also artificial intelligence. Typically, they do it from statistics. And I explain what is the main difference when we do this reduced modeling as we go along. Since I have a nice jacket, I want to take care of that so it doesn't get crumpled. Anyway, so the idea is like, this is the outline of my lecture. After introduction motivation, I'm going to cover now. I'm going to talk about homogenization. This is more successful reduced modeling, then stochastic homogenization to bring in probability early on. Then to talk extensively about modeling of fracture, either structure level or material level, and then to go into the reduced modeling, how to build this for different type of classes of problems. And at the end, discuss some of these dynamic effects and so on and so forth. So as I said, lots of this work has been done while I was in charge at École Normale Supérieure, Laboratory of Mechanics Technology in Cachan, of the civil engineering part. And we worked on this nuclear installation. So what you see here, this beautiful structure, this is cooling tower. So every time I did lots of work on shells, I would have been able to do lots of research on that, but they say we don't care about the structure. This can collapse every year. We just build a new one. What is really important is this ugly little duck. This is called this protection shield structure for the nuclear reactor. So this one should not collapse. And everybody nowadays knows what it means, but this structure collapsed because Fukushima happened in the meantime. When we started working on that, nobody was thinking about Fukushima. In fact, the main goal was the following. We said that even if you don't have a failure, you hear these things, you know. And then basically you're catching this moment here. I'll try to stop it at the right time. Oops. This is it now. You can see here this water, this is actually 1/4 of the model, which was built in Sandia, not the real size model. So already you have a size effect because you're getting the failure mode, the smaller structure. And you are after this type of failure when already the cracks are big enough so the water can start pouring out. What that it means? That means that if you have a leakage of radioactive substances from your reactor, everybody in France lives nearby some nuclear power plant because the 80–90% of electricity comes from nuclear power plants. So we have more than one. So basically, if it starts leaking, you're going to be having a very serious pollution for people's health. So you have to come up with a result which is called crack spacing or opening, because that actually conditions what kind of cracks you're going to have. So basically, if you have one big crack, it's like you have no protection shield. If you have small, tiny cracks, then you can hope to kind of spread, to stop spreading these gases into that. So at the time we worked with Electricité de France, first we worked with Université de France, then we moved to the scientific institute of the Università called Commissariat d'Énergie Atomique, and after that to the government, the research institute called the Institut de Radioprotection Nucléaire, which actually decides the laws that impose on that. So we're doing better and better job, we're getting more and more clients, and some of my former students, you can see many of them worked on that, are now working in this environment. Actually, Christophe Cassiotti is probably one of my best students. His name sounds Greek because his grandfather was Greek, but he's 100% follow French from Brittany. Actually, he is now he's actually the director of the department who decides whether a particular nuclear power plant will be operational or stopped. So I'm very happy that Christophe, such an intelligent guy, is a big boss because I can sleep more soundly in France. I'm sad that if he stayed with research, my H index would have been twice as big than it is right now. But what can you do? Everybody looks for their own fortune. So this Electricité de France, and the job was not the only one. Now, with the nuclear energy being a little bit compromised, you have to look into the new application domain. So basically, we are thinking about transportation because transportation has to be completely redefined, especially probably the most successful European company is this Airbus, which is a joint French, German, British, Spanish, and all kinds of vectors. And basically, they have to fight this Boeing challenge. Boeing built the largest airplane from composites, 787. And so this airplane is something that you cannot be testing. Also, if you wanted to renewable energy, if you want to produce more electricity, happen to be a challenge of having 10 megawatt per year. If you take a 10 meters per second wind, you need roughly 100 meter long blades, which is longer than the largest airplane that Airbus ever built, which is A380 with 80 meter span. So basically, for the moment, they cannot be testing this in a real condition because industry up to now likes testing this in person and say, now this is certificate. We test the real structure and this is it. But for these things, you cannot because the largest testing facility, which is Toulouse, so-called test, this is located in Toulouse, which is headquarters of Airbus. They can be testing only 32 meters long wings. They cannot go beyond that. And typically, they can be testing also only static tests in the cantilever beam. But in reality, if you have been in a turbulent flight, you know that it's not statics, it's really lots of dynamics. So what are you really testing? In reality, that's not quite interesting. So this testing pyramid comes from aerospace industry. Mach, who is one of the Airbus guys, I heard him on the French Congress of Computation Mechanics. He said at a certain point, before testing a lot on the structure side with the full-size test, we're going to be doing lots of material tests and then do low computation to climb up the scales and replace testing. So you're going to go faster. But what is forgotten there, when you go from material scale to structure scale, what is the role of probability? In other words, when you talk about composite materials, there's actually something called size effect. And as I said, failure modes are not the same, even if the composite materials are the same. If you have a small structure or if you have a large structure. So I want to expose this a little bit as they go along. So this is the kind of contribution that we've done in a computer methods, plan mechanics and engineering, a recent paper that just came out. Another one coming is Spring in Nature Applied Sciences with my colleague Herman Matisse and many collaborators. Some of them are even celebrating birthday. So happy birthday for those who are celebrating it. So basically, the idea is like, what is the challenge? Is to have a predictive, heterogeneous, multi-scale method. This multi-scale method has to be spanning all the scales which are important for durability of those structures. So to make the things very specific, it happens to be on the hydration of cement you have to have, for example, these tools that are produced in Nice. Nice is National Institute of Standard Technology in Washington, D.C. And they decided that the typical characteristic scale of a cement-based material is located at 100 microns. So what you see here in beautiful colors are 16 different phases of product of hydration of cement. And this is really like a random process, because you start water from top, from bottom, from below, from left, from right, and you get different chain of chemical reactions. So these processes, these 16 phases, happen to be arranged in a very different way. Then you go to the cement, where everything becomes kind of blackish and whitish to get this type of thing to obtain what it is. And then you go to concrete, where they have an aggregate as opposed to cement. Then you go to reinforced concrete, because you have these reinforced bars and so on and so forth. So you end up having to span something from micron, which is 10 to the minus 6. So if you have a 1,000 meter structure, this is no big deal. Bridges of 1,000 meters are kind of standard. Big dams of 1,000 meters are also standard. So you have to span from 10 to the minus 6 to 10 to the plus 3. It's the same like a world of nano, 10 to the plus 9. But the only difference in nano, you start with Ising model, which is very simple. It's 1 or 0. Whereas here you start with the 16 different phases at the level of microns. So you really have to start modeling in a more different way. And this is where the probability comes in. And it really helps you through this model. So basically, today, to be able to meet such a computational challenge, because if you go to very fine scale, you have to cover 10 to the 9. You really have to have some kind of more efficient computation than just a brute force approach. So today, this is really like a big work, and it comes from Herman Matisse, my colleague who's mathematics, and he follows those things. They're very much inspired by artificial intelligence, but they're building reduced order modeling for statistic and probability. And many of the works are cited here, but none of those works are very much of interest if it comes to fracture and rupture, because they typically study smooth phenomena like in fluids and things like that. So basically, the only exception is the late Ted Belichko, who was working in a very ad hoc manner to produce this reduced modeling. It's called it multi-scale aggregating discontinuities, MAD, like crazy. Ted had a really name for these methods. And this was really just 2D mesh coarsening, getting Q4 element with our glass to get from very fine mesh. So this is fairly ad hoc with what respect to what we are trying to do here. So first, reduced modeling, I would say, be classical. So this is probably the most successful reduced order model. What is it trying to capture? If you look very closely to a material, you take a magnifying glass, microscope, and so on and so forth. Nowadays, this is being captured by the digital image processing. That means you glue some kind of film on top of your heterogeneous composite material, and you start making the experiment, and the film deforms with your material, and you can get the post-processing displacement field on that. In Kashan, we had a group working on that who are quite successful and really known, at least in France. Then you cannot get only like surface measurements. For some of things, you need 3D measurements. So you have a digital volume correlation. In other words, you kind of get the X-ray measurements on tomography. The only curse, you cannot do it on a very large specimen. And you can get the fine scale, what really happens in the microstructure of material. And that way you have something called the material point, a structure scale. And you have a, like if you have a magnifying glass, rather than naked eye of a human, you can see much more details of a particular material. And this is something that engineers called representative volume element, and mathematicians call this scale type of parameter. And in fact, I studied Patricia in her morning lectures. She covered very nicely all kind of world literature in this homogenization type of works. But I really, when I started all this, it's normal. I was working in France, still working in France. So you start by seeing what the big shots in mathematics and mechanics. And these are the biggest shots in the University Pierre Marie Curie, where Lyons, everybody who is anybody in mathematics was a former student of Jacques Louis Lyons, and everybody who is anybody in, let's say, among freshly retired people in mechanics were former students of Germain, because these are the main centers of mathematics and mechanics. And interestingly enough, you know, they're not collaborating too much. So I try to recover this by collaborating a lot with the colleague of mathematics, with Herman Matisse. So here's what mathematics did with the homogenization problem. They took a typical mathematics notation. This is your Laplacian. Let's say the A, if it's a scalar field, it would be a heat transfer type of coefficient, continuity coefficient. If it's elasticity, U would be displacement vector. A would be elasticity tensor. F would be the load. And if it's heat transfer, this is heat source. So what they assumed, they said there are two scales. There's one scale, how this, let's say, tensor, which is characterizing material, varies. And this is characterized by some kind of asymptotic development that is given by this parameter epsilon. How do you pick up epsilon? They never told you. But they have an assumption that this is actually epsilon. So what they do is, in order to get corresponding reduced modeling, they have to solve this equation, which is kind of a cell problem, to provide some kind of a homogenization type of function, and then plug this function to that, and here you get your homogenized elasticity tensor, if you want. And basically, you replace this problem with this elasticity tensor varies like crazy because it's a composite material which is very heterogeneous. By the homogeneous equation, where this elasticity tensor is constant. And this is the sense of this asymptotic analysis. That means you express your displacement fields as a function of a slow varying coordinate x and fast varying coordinate y, and you can actually then build the systematic development of this in math way that I'm not going to go into details. Mechanics people did something which is more intuitively clear to mechanics. They said, if I don't see very well, I see a material point. And if I see much better, that means under microscope, I see that it is not the point, it has the whole world. And so basically, this is this representative volume element. How big is this element? Nobody tells you. But you have a representative volume element. Sufficiently representative, what is the microstructure? Again, what is sufficient? It's not so clear for all the times. And so basically, then you average, you solve the boundary problem of this whole new world, where you have a new coordinates, you can see the size. You solve the average strain and the average stress. With the big M, this is macro scale, and small m is a microscale. And if I do the large deformation, this will be like deformation gradient. This will be first periodic of stress. And then basically, I'm replacing the scalar product between conjugate stresses and strain, which is P and F, at the macro scale by the corresponding integration at the microscale. This is called Hill's principle and Mandel's principle in France, and so on and so forth. Now, if you're solving the boundary problem at the microscale, you need boundary conditions. So, of course, you have two choices. Either you make a Dirichlet boundary, that means you impose displacement, or you have a Neumann boundary, that means you impose the stress. It happens to be that the result for the homogenized stress tensor, the elasticity tensor is not the same. Here you have so-called upper bound or void bound. You have the most stiff, possibly elasticity tensor, and here you have a lower bound, which is Roy's bound, which is the most soft. Reality is between. If you don't take neither displacement nor stress boundary condition on this representative volume element, but you take periodicity boundary condition. That means if you move on that side, after this, you come to the other end of boundary element, you have representative volume element, boundary has to move the same size. And if you have stress, again, you have periodicity of the stress. Under this condition, you can solve the boundary problem and the representative volume elements level, and you get your homogenized elasticity tensor. It happens to be that the result by doing this periodicity boundary condition, you actually get the same result from mathematicians doing asymptotic analysis. It was really interesting. Those groups were active at the same time in 1980s at the same university, Pierre Marie Curie. One was mechanics, people were German and his collaborators. The other was Lyons and his collaborators. And they actually never really talked to each other, math guys and mechanics guys. So we really tried to correct this and do a little bit better job. And that's what I did. Then when finite element became a main, let's say, computational tool, we switched to something called numerical homozygation. Typically here you show the, let's say, 3-point bending testing. So you have a macro scale mesh, which represents your typical specimen that is being pushed into 3-point bending test. And then at the level of each and every Gauss point, those who study finite elements know how it works. You have your interpolations, and then your computation done by numerical integration points. So at the level of every Gauss numerical point, you build your representative volume element. And you have this interpolation at the fine scale, micro scale, with the coordinate called y. So when you're computing now results, you basically have a macro scale. That means the equilibrium equation done in the weak form with the macro scale displacement. These are displacement of these black nodes. And then you have equilibrium equation of these micro scale displacement. These are displacement of these tiny white nodes. So basically, on top of that, you have these internal variables. That means at the fine scale, you're looking for the explanation how these things are actually being computed. So basically, the problem there is that sometimes the things don't go very well. This method was first suggested, this numerical sort of homogenization was first suggested, at least in France, by a colleague of mine called Fayel. He called it finite element square. I really regretted he took the name because you'll see the method this suggests would really more deserve to be called finite element square. But anyway, the name was taken. And then it was used by very well-known people in Germany, like Riegers, his collaborator Studi. And for example, they looked into the case where the macro scale is kind of heterogeneous. They build the damage and plasticity combined. And so they had the interface within the plastic matrix here, and damage would be inside this hole. So the real failure mode here is this sort of J2 plasticity failure, which is shear bands at 45 degrees in this type of tests that are typical of metal type of matrix. However, here, when we do this smearing in 5-times numerical integration, we don't recover this. We start recovering something that looks like a mode 1 failure. And what is that? We'll actually explain this in a moment as we go along and study this a little bit more thoroughly. So if none of these homogenization that are done in mathematics with asymptotic analysis or with the mechanics with this representative volume element is working, we can try for stochastic homogenization. So if you didn't study probability, one would need really like 2-hour lecture just to introduce probability. I hope you did study a little bit, and I'll try to keep it as simple as possible. But the idea goes as follows. I'll still stick with numerical homogenization, and that means weak form is computed here. This is internal forces that are stresses times the virtual displacement. And here are the external forces that are either volume force or traction force. So let's say symbolically, I can write this as some kind of a evolution operator. A times the, depends on the parameters P of omega. And if I really want to refine this, I have to distinguish different scales. In other words, I have a microscale where these parameters P lowercase m handled as random field. That means they vary with a small coordinate y. When I have a really detailed representation, and omega. Omega is now a parameterization of probability. This is your typical probability space. That means all possible realization, what can happen in this. And then you have parameters at the macro scale. Some of them might be deterministic, and some of them could be unknown, random. And this is the kind of idea. I want now to identify these parameters there. I call them Q of omega. So the problem I'm solving is this one. These are evolution equations at the micro scale. And these are evolution equations macro scale. They look very much like the equations that I had here, only written in different notation, okay? And so basically they are written for every different realization. That means every time I test new specimen, I might have a different result. And that's often the case. None of the two experimental results give you exactly identical final decision. But what I want to now to compare these two scales, fine scale and large scale, is in terms of quantity of interest. In other words, formally, this problem is not that you do whatever you want. You actually want to get some result which is of interest to you. Typically, what you are really measuring from these two scales. One could be internal energy. The other could be dissipation. And you're just happy if two scales would have the same internal energy or the same dissipation. It doesn't mean that the displacement field of these two will be the same. Definitely they will not. But if you care about energy and dissipation for the fracture, these are the most important details. That's actually what you're trying to get. So how do you go about that? Well, you have to work on something called Bayesian updates or Bayesian inference, which basically turns this inverse problem of identification to obtain the parameters at the macro scale that I'm looking for, their probability distribution, into the direct problem of Bayesian inference. The way it works, I enlarge the problem of identification into the coupled problem of mechanics and probability. So I start here incremental procedure that you go for every new experiment I make. In other words, I have a loading program which is parameterized by this pseudo-time parameter t that goes from 0 to uppercase T. And you have a measurement number 1, measurement 2, measurement number n, all the way to the final measurement, which I call the uppercase T. So you start by the first step. You get, let's say you predict your observation. In other words, you take the value of these parameters you already have. This could be something somebody very experienced gave you that. It's so-called forecast. And then you solve the problem to see what macro scale would give you for this. And then you really take this type of new procedure, and you really work out with the let's say the parameters in the micro scale, because now we have displacement at the micro scale. You know what these parameters are, and you now solve the real measurement type of thing, which is obtained with the new value of these micro scale parameters, p little m. And then you have to update. Basically, you have to compute posterior or simulated version of this distribution of these parameters, which is now called n as opposed to n minus 1. Please recall this computation in terms of probability goes with respect to these independent uncorrelated Gaussian variables. So all these stochastic integrals could be computed in a very efficient way. I'm not going into details about that. There are two ways of how you actually do this update of the measurements as opposed to previous, let's say, forecast and so on and so forth. One of them is called Markov chain Monte Carlo. It was really the first historical method. And the second one is called what we actually worked on with Matis and his group, Gauss-Markov-Kalman filter. So basically, the things goes in a nutshell like this. The parameters that we are trying to identify, which are these macro scale parameters, will be identified as random variables. That means the values that are changing of particular realization with different distribution. The easiest place is the Gaussian. So you have an average value, a standard deviation. Everybody knows that one. So basically, a random variable is characterized by it's a function, and there's a probability measure, and there's this function. So Markov chain Monte Carlo is changing probability measure, while this Gauss Markov-Kalman filter is changing the function and leave the same probability measure. So how does it work? First of all is based on so-called bias theorem, or how you build so-called conditional probabilities. So bias theorem is nothing else, but if you have a probability of the measurements as opposed to probability of these parameters IQ, you're looking for the intersection between those two. And so basically you can say that the probability of intersection of these two sets can be built as a probability of IQ given my times the probability my. That means my has happened, measurements has happened, then you're looking into the probability of IQ given the measurements, multiplying these two, you get probability of this one. Or the other way it would be like probability of measurements given IQ, multiply probability IQ, again you get this one. So this is nothing but saying I'm getting the probability of intersection of two sets. So if I have a cross correlation between those two things, I can do that in a second. But normally I don't, because one thing is to have measurements, the other thing is to have macroscale parameters. These happen to be quite different things. Then I had to go iterative. And as I said, Markov chain Monte Carlo, you start with some kind of prior, then you actually, this is a prior that is given here. And then basically I'm trying to update it to the posterior, and the procedure would be changing in the process, the probability measure. With a Gauss Markov-Kalman filter, I keep the same probability measure. In other words, I'm going to be constructing this in terms of Hermite polynomials in omega space. This is the space of all realization. I never change that. I'm just changing the coefficients as I'm multiplying these polynomials. So it becomes very fast. Once you establish these polynomials, after that becomes like deterministic computation of a copy of your own problem. And this really becomes even better than usual Monte Carlo type of method, because you have a better coverage of the probability space. So how do you compare these two? First of all, when you run to the end, it needs many increments to converge, because every measurement gives new information. Sometimes if you have completely useless information, it doesn't give any improvement from what you have. But you have to have pertinent and useful information to improve those things. So it happens that Markov chain Monte Carlo needs many, many iterations to converge. And this is order of magnitude. And I say order of magnitude is like 1,000 times less efficient than the Gauss Markov-Kalman filter. So we're going to really study that one much more in detail. What that one does, as I said, is basically first observation is that conditional probability could be built with the conditional expectation. What is conditional expectation? Expectation is the average value of variation of some kind of probability. So you take your random variable, you take multiplying in the probability space with the probability distribution of this variable, and you have expected value. So expected value is just computational integral. It's very easy to compute. And basically, you express this, you try to get the best improvement by comparing what you have in terms of expressed in this type of format and the one that you kind of supposed. And as I said, this probability was expressed through this Hermite polynomials. And basically, you next assume that this Bayesian update could be cast in this manner, where you actually split what you already have. That means the forecast times what is called Kalman gain times the update with the basically what you have with your measurement. That means this is the value of the measurement. This is the value of the what you get from the forecast. It so happens when you have Hermite polynomials, this Kalman gain could be computed as a covariance. This is how it varies from one side to another of the measurements and the covariance between the parameters and the measurements. Again, you have to be able to access this, but this could be all expressed by using the consistent, let's say, probability distributions. In particular, you can think of that. If you have your parameters represented in a random field, that means I have variability with the space x and with respect to realization omega. I have an average value, which doesn't vary on the realization. That means just the average of all the experiments I did. And then I have this residual, which is varying with respect to this average. And so basically then my displacement could be constructed by using the same type of random fields. Only the difference would be that I have a, let's say again, space variation times the what you call it, realization are now captured through this variability with respect to parameters is maybe not enough. So I need the higher variability of the result that are really of interest to me, like displacement field. And so you can think of that like in dynamics, you have a space and you have time. And then you have one discretization of space, one discretization of time. It's the same thing here. I have discretization of space. This is called H method. I divide my domain in subdomains. This is the finite element that it does. And in probability, I just have a one big space. It's called space of all realization. In order to capture everything what happens there, it's hard to divide this realization into blocks. Then I'm not going to have every possible realization. So instead of dividing this into blocks, into elements like I do in finite elements, I actually cover this with so-called P method. I have a higher and higher degree of polynomial capturing all this. And so my computation of this, let's say, random field becomes the following. I have expected value of something which looks like a stiffness matrix interpolated in this way, times the nodal value of displacement for each and every realization equal to the nodal value of loads, which are computed again this way. And then once I computed this nodal values for all the realization, I can simply obtain the, let's say, internal energy as the product between this displacement and this G here, which is the solution of which is my force base. So this way I have my quantity of interest at the microscale. This is the most intense computation. This could be replaced by the experiments at the microscale. But here, in this case, we are actually doing the computation of the experiments. How does it work? Well, if you're interested in identifying the probability distribution of these elastic coefficients like bulk modulus K and shear modulus G, you can see that it does converge very quickly. In fact, it converges so much quicker if your prior is better. So sometimes rather than taking this prior blue, which is an expert opinion, and maybe this expert doesn't know everything, so he gives you a very large standard deviation. When you do first computation, you can take this computation result to be a new prior, and you get better and better starting points, so you go into convergence much more quickly. And you can see also here, this is the same type of result, only presented with the confidence interval with the 95%, let's say this type of results. And you can see that as make more and more measurements, especially if they're pertinent, if they're correct measurements, you can actually reduce this to a deterministic value, which means this is like homogenization. What is really a big advantage of this, I don't have to talk about neither a representative volume element or what you call it, this asymptotic type of scale separation. I simply keep grinding the new numerical results and I get better and better with it. This is what they do in the artificial intelligence. They have like a quick Google type of search of how many people think this is good or this is bad, whether COVID is artificial, whether China brought COVID or something like that, and then they build the model. Often you cannot really build the model if you don't have some intelligence. And basically this is really what we have, the advantage. We can do experiments, we have the knowledge of the previous stuff, and you can do much better than just artificial intelligence. At least that's what I hope. So basically, this is as much as I said, well, elastic response, you can really converge down to the deterministic value. That means homogenization works. If you have elastoplastic, here we did this at the same story with plastic and damage, as many measurements you make, you cannot really converge perfectly. The reason is that in some part you're elastic, in some part you're plastic. So basically, you never know which one will be elastic, which one will be plastic, depends on the loading program. But you can really make it to as narrow as possible if you do that. So let me go further. Now I started fracture. So you can see the role of probability. This was really like a crash course in probability, only what is needed for us, 5 pages. If you never studied probability, I'm sure this is going to be tough. But if you study probability, this could be quite useful for your remarks. Now I hope mechanics is much closer to your background. So I want to study a lot different models of mechanics in terms of fracture. In other words, I have a structural level model, I have a multi-scale material level model, and I want to explain those two to start with. So why is the problem when I have a fracture? This is your specimen. I'm taking a very simple result. If you do structural mechanics, this is the simple result you can have. You have a statically determinant bar, you fix it on one side here, and you pull it on the other side force. Along this bar, the force is constant. If the cross section is constant, the stress is constant as well. That means whatever happens in every point of my bar, the stress is constant. You cannot have better result than that. However, bar happen to be heterogeneous. So one of these sections is maybe slightly weaker than all the other sections. So I put this section to have a strength of 99% of all the other sections. So what happens? If I have something that can break, I realize that I run the numerical computation that basically this break will mean that stress starts going down because it starts breaking. You have something called fracture energy. As you go down, you reduce the stresses down to 0. So if you run this numerical computation, your finite element code, you take any code. If you have elastic material and you take a modulus, which is normally called hardening, put a negative value, so it becomes softening. That means the stress goes down once you pass the limit of elasticity. This is typical of fracture. So basically, the idea is like what you're going to obtain from the normal finite element code. The more elements you put, the steeper you go down. If you put here, you have a 3, and then you have a 7, and you have 15, and so on. The more elements, and ideally, if you put the infinite number of elements, you're going to go up and you're going to go down by the same length. And normally, you know that the area underneath curve is actually dissipated energy. Every material has a fracture energy that I have to put in order to break this material completely. I can here tear the piece of paper for those who are, and they say that there is a fracture energy for my piece of paper. And typically, this is the most reliable type of measurement. So basically, this is really something that I want to use. And here's the reason why it is really such an ill condition, because result obviously does not converge, because the more elements you put, you get different answers. They taught me in finite element first course, if you put more elements, you get better result with finite elements. But here you get more ridiculous result. And the reason is here. If you have this weakened element, if you have only 3, that means this element will be have a large plastic strain, and all the others will be elastic. Imagine you are here somewhere. So this element has a very large elastoplastic strain, and the others are unloading because they never reach beyond, they never reach sigma y. This element started at 0.99 sigma y. He immediately reduced the stress down to 0.98, 97, 96, and so on. And then the other guys remained elastic. And so basically, if you take now a finer mesh, this element will be smaller and smaller, the one that is breaking, and all the others are elastic. And since it's smaller, you compute dissipation by integrating over the length of this element, you have a smaller and smaller dissipation. So this was fixed. You need something which is called stress discontinuity to really represent something like a crack inside the element, and this is what I'm trying to explain there. We learned this a long time ago when I just came to Kashan in year 2000. Electricité de France had a big benchmark, and I had really to do good because we wanted to have lots of contracts, like you see, we did. And so what happened, they put many of these benchmarks. It happened to be one of the most difficult was this Noor Mohammed double-edged notch specimen. It was a thesis in TU Delft. The guy tested first like a shear type of this block of concrete, and then he pulled it with the intention. And so it happens that the stress was very heterogeneous, already because of these notches, and secondly, because the loading program was non-proportional with the shearing and then tension. So what we could do, we used the damage model from Mazar, because when I came to Kashan, I inherited 4 of the lecturers who were trained by my predecessor, Mazar and Pishli. So I said, okay, what you know to do, let's use this. And so basically the damage model of Mazar is the simplest damage model you can imagine. It is introducing the notion of the damage elasticity tensor. In other words, if there's no cracks, elasticity tensor is the nominal value, which is called E. When there's crack, elasticity tensor has to be multiplied by 1 minus D, where D has to be from 0 when there's no cracks to 1 when there's crack. What's wrong with this one? Well, it's isotropic damage. It means when you multiply the whole elasticity tensor with 1 minus D, you mean you reduce the resistance to each and every direction. And this is not correct. You have to be really directional with respect to cracks. In cracks, you have to reduce resistance perpendicular to the crack, and along the crack, you basically have no problems whatsoever. So what we did here, we fixed the elastic response, and we fixed the first failure. And you can see the green was what Mazar model predicted, and the red is the experiment. You can see the experiment was much more ductile than this. So it was complete failure. It took us many years to get not only force displacement right, but also the crack. This is experimental result of measurements of crack. You can see these, they are almost perfect to follow what really is happening in terms of cracking. But it's not the same model as Mazar. I'll tell you that one what it is. But it's not only Mazar. Everybody did very poor job, and everybody who's anybody in France was competing. Teams from Spain, from Germany, from US, and my collaborators, De La Place and one guy from Electricité France, they compiled a special issue of French Journal of Civil Engineering, and this is your experimental result. So many people either fixed, and it was known. So you could either fix the ultimate resistance, or you try to fix the damage. If you fix one, you don't get the other one right. So what went wrong? Well, people are using the finite element. In the finite element, every element has homogeneous strain field. Let's say you have a constant strain triangle. So whatever you do, once you start failing, this element can only go berserk. And this will be the same thing like this bar that I was showing you. The more elements you put, the smaller dissipation you're going to have. And basically, you cannot repair unless you change paradigm, like you change way of thinking completely. So what did we change? We said, forget about standard finite elements for fracture. We have to do better. What is better? We have to separate complexity. And each mechanism that happens in fracture has to have its own criteria. And then basically, you have to distinguish between the dissipation in volume and dissipation surface. That means for the crack. And basically, this is something that I'm going to explain in detail. And then it is not enough to use standard finite elements. You need a better interpretation. You need finite element modeling type of kinetomatics and so on. And then also the final decision, what is the fracture parameter? So you take this GF. So a second point here is that you're using so-called operator split. What that means, if you have now many phenomena you're trying to compute, you're basically integrating this in time with the given loading program, which is specified by your T parameter. And you can say that normally this goes if after one step and second step and so on and so forth. And if A is constant, you get exact solution here. So what is the operator split? Imagine if A has a one part and the second part, and you're not running this simultaneously. The solution is given here. It's exponential A1 applied to the value at Tn, and then exponential A2 applied to this product here. So what we do is basically, as soon as we're done computation at Tn, then we stick it into the second computation, and we carry on that. Here's the illustration. If you have a classical plasticity with hardening, in France, this is called standard generalized material. It was done in a very well-known paper, Nguyen and Halfen, in 1975. You can explain all the variables to be displacement, from which you compute total strain, then plastic strain, and the hardening variable. This plastic multiplier just saying whether you're elastic and plastic. So when you're running computation, you have to evaluate, compute evolution of your displacement field, then evolution of your plastic strain, and then finally evolution of your hardening variable. Typically what you do, you freeze hardening variables and plastic strain, and you just compute evolution of the total strain. This is called the elastic trial step. And then if you happen to be plastic, then you freeze total strain, and then you compute corresponding evolution of the plastic strain and hardening variable. This is called the radial return mapping for very simple models and stuff like that. So I'm actually not computing all these things at the same time. In mathematics, this is called constrained optimization problem. And this type of approach is called interior point algorithm. In other words, your stress field always has to be plastically admissible if you really want to be looking for the minimization. The final step, if you want to really have this applied, there was lots of dispute on thermodynamics between people in different type of domain, whether thermodynamics applies for fracture. Well, under which condition it will apply? Basically, it will apply if the rate of evolution of these internal variables is much, much faster than the rate of evolution of the other variables. In other words, you're going very slowly increasing the stress and strain in order to introduce the rupture. But when the rupture starts, the crack propagates very fast. And really, it has to be fast. This could be measured by, let's say, if you have a viscoplasticity, then you have some kind of like a viscoplastic organization or plasticity problem. And you can see if you increase the strain beyond what is the limit of elasticity type of in terms of strain, the stresses will first go above yield stress, and then after some time they will go relax to the yield stress. And so the smaller time for this relaxation takes, the better it is for these internal variables. So you have something called rate-dependent plasticity, where this plastic strain relaxes to sigma I instantaneously. And this is really the kind of separation of scale is something that we do. And this is how you can actually compute. It is important to know, although it's a little bit subtle to understand for many people, but think of that deeply. You have my book in 2009. There's lots of things explained there, especially first chapters are complete, but later are not complete. So you have to start reading from page 1, and there's 600 pages. So it's maybe not too much. So what did we contribute to that? We actually brought the structural point of view for the softening problems for the case where not only I have this crack, but I have so-called fracture process zone. And this is typical of massive structures. If you want to bring down one of these bridges, unfortunately, some of them collapsed even in Italy, and now in whatever US and so on and so forth, it is not, let's say you have a statically indeterminate structure, you have many, many, many columns. It could be enough to have 2. So you have to damage all these columns completely, and then only then you will come to the ultimate resistance of the structure. So damaging this particular column, that means you bring this to the peak of resistance and you go down. And so all this dissipation at the level of structure will be still where the structure is hardening, because global response to the structure is still hardening. This is so-called fracture process zone. Symbolically, I represented this as a bunch of these tiny micro cracks. And for the concrete structures, contribution of fracture process zone is very important. Well, in linear fracture mechanics, you typically neglect that. You have criteria as Griffiths, who doesn't talk about fracture process zone. But in reality, even every material has fracture process zone, only it's very tiny, and contribution is almost without any importance. And that's why people don't talk about that at all. But if you really want to be consistent, you have to talk about that. And this is the kind of result I really want to explain here. Now, Professor Patrizia Trolucci this morning really nicely presented all these different things. So I go very quickly here. There are all these different methods that can handle these localization problems. First, artisanal, what we call in France, that means just ad hoc type of, was a crack band approach. It was, as far as I remember, the first was along these lines with the Wieland, and then Bajant and Bichenich and so on and so forth, where actually just compute kind of crack band model. You compute what kind of dissipation you want to have, and you have a size of the element adjusted to the desired dissipation. Then you can do cheating with this viscosity. In other way, instead of plasticity, I introduce viscoplasticity, and I get the viscoplastic dissipation and plastic dissipation. But either one or the other is really cheating. If you really want to do correct, then you introduce this internal length scale that was presenting this morning. In other words, it's Costera media. Unfortunately, it works mostly for mode 2 failure. That means under shear. But masonry often fail under mode 2, so this is fine. In mode 1, Costera doesn't work. So then they have no local, but again, remains on what is the internal length. It's, as I said, when I talked to Pijay Kabo, when I replaced him, and he was coming for administrative discussions to Kashan, he was saying this is 3 sides of aggregate, but aggregate is a bigger size and then small size. In EMPA or Fuller curve, you have everything mixed. So which one is it really? You need some kind of probability to mix that. Then there was gradient plasticity models, which show difficulty of deciding where exactly is plasticity, where it's not, boundary conditions, so on and so forth. So starting 90s, interrupt. Yeah. Yeah. Well, as I said, I can. Yeah, I can go. We can discuss that outside. Yeah, if you want, we can discuss this. Yeah, we can discuss that. But I can give you the papers where these guys who really studied Costera. It's not only the boards. There's one German guy called Mulholz that I talked to personally in Germany in one of the specialized meetings. He came there. Otherwise, he's in Australia. He worked a lot for this mining industry, where they had really soils and stuff like that. But as long as you have failure in mode 2, and I'll show in masonry, you do have failure in mode 2. It's shear. It's just fine. Costera is perfect. In mode 1, nobody's doing tension test on masonry. It's crazy, so you have no problems whatsoever. There's no point of discussing. But we'll go back to that if you want to, not to break the flow of my thoughts for the other guys. Anyway, starting in 90s, people started using this kind of discontinuity models that either introduce strain discontinuity or stress discontinuity. And there are many names that made a nice contribution, like Ortiz, Belichko, Simon, and so on and so forth. So basically, what we did there is the following. Again, I'm not going to repeat what happened, why do we have this softening, but what we really generalized, it was in the paper first appeared 2003 in Computation Mechanics. This was Crisfield issue. Mike Crisfield was really a good friend of mine. Every summer he was spending in, like I came in summer, end of the summer to Rome. Mike Crisfield was coming every summer to France, and he would stay for dinner, maybe even spend the night, and then move to the south where he was spending his summers. And then he passed away, unfortunately, to 2003. So it was a special issue dedicated to him. So in this issue, what we understood is how to get the failure of a massive structure. In other words, a structure which has a sizable contribution of fracture process zone, which still has hardening and then softening, contrary to these guys who had just elastic and then softening. So it happened that you need a volume dissipation plus surface dissipation. This is the stress opening, what your stress vector that works on crack opening. And basically, this could be worked out under some kind of a stress orthogonality condition, which is really how to connect these two scales. If you fulfill this condition that basically says that the work in the fracture process zone of the stress should be the same as the work of the stress vector on the crack opening. And basically, that is actually how you connect these two scales, comparable to kind of the best type of connection you can have. So basically, for what this model to handle, you need the following ingredients. You need elastic response, then you need hardening response, and finally you need softening response. Hardening response and elastic response are built within continuum mechanics framework, whereas the softening response is basically force versus displacement. Only you mix them together thanks to using Dirac delta functions. This is the way it works. First, you build your equilibrium equations, and you say there's now discontinuity, which is a crack. And in this discontinuity, I have a continuity of stress. In other words, until you fail, the equilibrium equation has to be valid. I cannot have jump in stress vector on one side. It has to be the same on the other side. And so introducing this into the weak form, I get the proper formulation of the weak form where the failure started. Then for kinematics, I need some kind of jump. This is done by the Heaviside function, which simply has jump at this particular point in order to be able to include the crack opening inside my kinematics description. Typically what is done, rather than just putting Heaviside, what Heaviside would have done inside one element, it would then influence all the displacement to all the other elements. So we do this little trick that we actually subtract from this Heaviside function another function which we call the phi of x, which is supposed to eliminate influence of this crack at the nodes of the element. So it could be attached to any other type of element without perturbing the rest of the elements, because crack typically stays inside this element, and you're handling this. So at the end, you decide that your displacement field is built this way. And if you take your gradient, symmetric part, you get your strain field, and it's done with the regular part, and it's done with the Dirac type of function. That means this is the strain that corresponds to crack opening. Final choice is the constitutive modeling. So in the thesis of Delphine Branchi, we did both plasticity, which corresponds to mode 2 failure, and damage, which corresponds to mode 1 failure. So basically, when do you start the softening? There is something called acoustic tensor that you build from your elastoplastic tensor. And when it happens that this acoustic tensor becomes singular, you get a solution that basically gives you what is the orientation of this tensor where you actually have the crack. And M is the type of the mode which happens. So if N and M are, what you call it, parallel, that means you have a mode 1 failure. And if M and N are orthogonal to each other, you have mode 2 failure, which is typical of metals. And so is in masonry and so on and so forth. So basically then you can build, this is in damage, you can build your continuum part, you can build your discrete part. All the ingredients are there. All the variables are like, you have a strain, you have a hardening variable, and damage compliance, which is typical internal variable for a damage type of model. Then you have this part when you, let's say, when the state equation is given as sigma stress is equal to D minus 1 times epsilon, you have a damage function. This is typical of isotropic damage to start with. And then you have this discontinuity type of handling of damage, which says like a mode 1 failure, sigma F, and then sigma S would be mode 2 failure of damage. Of course, then you have this hardening and softening variable evolution, corresponding dissipation and whatnot. So basically, if you want to implement that, the kinematics of your element has to be enriched. It is not, this is your constant strain triangle, but it is not enough to have just linear polynomials. You have to have something that describes the jump of this. And this is basically describing the crack inside this element. And so then every element which is designed by the crack, you have to have not only like a contribution of this element to global equilibrium equation, but you have to have the local equilibrium equation, which are connecting this stress of kinetic condition, connecting stress inside the element with the traction, which is working on this discontinuity. And so basically this could be handled very nicely inside the finite element computation. Here's your global level where you're computing the total displacement field. And here you use a computation of the crack opening, U double bar. And for each and every Gauss point, you have computation with plastic strain, damage variable, and whatnot. So this could be implemented inside any standard finite element code. It just takes changing the element. What does it do? Here's the demystifying. When you have methods like XFEM, this is one of these competing methods for fracture, which is really taking linear fracture mechanics. So X is like extended finite elements, is describing the crack, and then you do computation on top of that. Well, this method doesn't do that. It does not describe the crack perfectly. In other words, if you have a coarse mesh, you have a crack which is 157 millimeters. If you have fine mesh, crack is straight line is 133 millimeters. So these two cracks are not the same. Obviously, I'm not doing XFEM. But if I look for the spacing diagram, Grossier is the coarse mesh, fine is the fine mesh. These two curves are on top of each other. And what is underneath the curve is dissipation. In other words, with this method, I'm capturing dissipation perfectly, exactly, for any coarse mesh or any fine mesh. And this is really the goal. As I said, when I want to measure something, I don't measure the crack. Crack is so random, there's no hope of measuring any crack. And from one realization to another, crack goes berserk. But the energy has a chance of stabilizing. If you have some kind of regularity in this microstructure, that means you can get the same energy by breaking specimen after specimen after specimen. And that's the most important actually. So basically, this is something of Nur Mohammed I like. We took a notch and then we did this non-proportional loading program. And you can see that if you have a fracture process zone, it's better to have it. First, this one is active and then this macro crack is active. If you only have a macro crack like XM, of course, you get completely different type of answer. It's not worthy. Another thing here, if we had 3-point bending test with the notch, you can see again, either coarse mesh or fine mesh, they're practically on top of each other. So it's really doing fine. This is just a two-side remarks. When we did geoplasticity, actually the first one we started with, if you do this simple tension test, plasticity fails in shear. So this is not the cracks, this is more like shear bands. You have a sliding in mode 2. From these notches, you have a fracture process zone, and then you have sliding. And then you use special interpolation like B bar to capture this non-incompressible response for J2 plasticity and so on and so forth. We also did masonry, even very poor design of masonry, because typically the bricks are what you call shifted to another. but we did a plasticity for the joints. This is simply more Coulomb or Drucker-Prager if you want, just sliding and then have a there. And then we had the blocks of brick to be breaking in tension, in compression, in shear, and so on and so forth. So contrary to many other homogenized approaches, we did this one. And in fact, we got really much better result. Experimental result is this one. Our result is that one. We can capture, if you want the peak better. This was a work of Roth and I think Lorenzo, who is now in Portugal. They did everything in the joints, but actually bricks also break if you look into that. And they didn't have these modes in there. And then at the end, we just have to stretch it a little bit. We have perfect. This was done in French review of civil engineering, so probably not very highly cited paper. It's too bad. It's actually a very nice paper for application in engineering. Especially in Italy, we have many masonry structures. So if I want now to do a better job with the material level, this was structure level, I especially want to capture something called size effect. The most strong advocate of size effect was Bajant, and frankly, I never understood his point. Typically, in these cohesive materials like concrete, the way you're testing your tension resistance is by 3-point bending test. You cannot put concrete into testing machine like steel and just pull it vertical. It will be crushed if you put it in testing machine. So what people do, they put 3-point bending. Here are 2 supports, and here's the force pushed in the middle. So you have lots of tension here, lots of compression there. Stress is close to 0 there. And basically, you have a heterogeneous stress field. In every point, you change stress. And then materials heterogeneous stress field, heterogeneous material, you can get anything you want. And Bajant, he's maybe the only guy who can do that. He miraculously said, well, this is the way you do it. If you have a small specimen, and D is supposed to be some kind of size, you have something that looks like a continuum mechanics failure. If you have a large specimen, you have something that looks like linear fracture mechanics. That means a crack, and that's it. I never really understood what does it mean to be small and or large specimen. You have this 3-point bending, because it depends what kind of material. If it's bending dominated failure, okay, you can say there's only one crack. But if it's shear dominated failure, because some materials are not good in shear, they can have a shear dominated failure, then you have a completely different ball game. It's 3-point bending, everything can happen. So we try to do better. What did we do better? Well, we didn't want to do this homogenization story, what they call finite element, although our stuff is frankly more close to finite element square than theirs. We call it miel. Miel in French is honey. It's like actually a colleague of mine, Herman Matisse, who called it miel. Mesh in element, multiscale method. So you take a macroscale formulation of this specimen, and then at one macro element, you build a mesh of these micro elements. You're going to take a different coordinate to integrate that. More realistically, it's like this. Basically, take a macro element, you fill it in with the microstructure. And then basically, you can say that the total energy is the macroscale energy, and then microscale energy. After microscale, I'm going to be computing my internal variables. And then, of course, I have this interface condition. They are replacement to homogenization, and I have the external load. So simplifying assumption, well, before simplifying, I can comment that I can do this combining with the digital image correlation. So instead of computing this, I can slam on this element a measure displacement field that comes from the experiment. And then I compute this at the macro scale directly from experimental result to say what will be happening in the structure. If I put such an element into the structure, I can have a redistribution from different sides. And that's actually what I tried to convince my colleagues in Kashan to do. We never got to do it because talking to experimental guys is very difficult. They have a different mindset. They have their own problems. So we never get to do it, but too bad we did. So simple assumption, we did it only computation-wise. We said that the external load is only at the macro scale, which is not a big deal, because if you take a specimen to be like a concrete, you take a dead load, you can homogenize that load, is not really a big deal. On the other side, the micro scale, I'm computing my internal variables, and that's important to keep at the micro scale. And of course, interface conditions are very important to handle. So here I have a threefold problem. I have a macro scale, micro scale displacement, and plus these Lagrange multipliers, which are introducing some kind of work equivalence between macro scale displacement, U with big M, and U with small m micro scale displacement. So when I do the variational formulation, I have 3 sets of equations. For the moment, I'm ignoring the internal variables. I'll come back to that in a short time. So for the fixed internal variables, I have variation for the micro scale, variation for the micro scale, and I have this interface condition variation. So imagine now what I need to interpolate is displacement micro scale, displacement macro scale, and this interface condition. So please note that the macro scale, I will only have the nodal values of macro displacement and the nodal values of this Lagrange multiple, which starts playing a role of the internal force directly on my element. So once I did that, I can actually do the finite element assembly. So that becomes something like a localized Lagrange multipliers that I learned from Casey Park, who studied a lot fluid structure interaction. And so basically every element or the macroscale could be handled separately. And you see as we go along how it goes. So here's the displacement-based coupling. I take this Lagrange multiplier to be Dirac function, which that means is basically if I move these two corner macroscale nodes and their linear distribution by the standard shape function for node element, all the other nodes of the boundary will have a linear distribution of the nodal displacement. Hence, at the microscale, I have to solve an imposed displacement problem where the variation of this displacement is known, is given from the macroscale, and it could be go very quickly. Another way, since I'm interested in bending dominated problem, if I take a stress boundary condition, then I choose a special interpolation of stresses which corresponding to something called Pia-Sumihara element, which is the best element in hybrid stress interpolation, predicting the response in pure bending. So this is the type of response in pure bending. Sigma XX varies linearly with Y, because this is the choice of bending. Sigma YY varies linearly with X, and then sigma XY is constant because it's bending. So I take this interpolation, I project on each and every side of macro element, and I have a corresponding interpolation for my macro scale Lagrange multiplier, which is going to give me stress-based type of response. So this displacement base will give me upper bound of stiffness. This give me lower bound. And the one which is stress orthogonality condition that we did with Delphi Brushley will give me the best something like periodicity. So this is just fantastic. So this is the way we execute. We have now displacement base, for example, to make it simple. I have variation of the displacement field macro level. At the macro level, I take corresponding interpolations. Here I choose my Lagrange multipliers to be Dirac function. So my linear interpolation of the boundary at the macro scale element with respect to the corner nodes, and it's all done. After that, I simply have to solve these two boundary value problems. One is very intense. This is a particular macro scale element with all the details of microstructure inside. And the other one is simply taking the value of these Lagrange multiplier interpolation parameters at the corner, using them as a, let's say, internal forces, and then computing, re-equilibrating between an element which is failing with respect to neighbors. We'll say, okay, now you have to take into that, and so on. Now, at the microscale level, of course, I have to compute my internal variables. This is something which is kind of a special computation. And so then I compute the corresponding stiffness matrix and so on and so forth in order to get a new prediction of the macro scale displacement, and I go along. This is perfect for parallel computing. That's what we've done in collaboration with Rina and Nikamp, who was working at the Institute of Hermann Matisse at the time. And basically, you can see you have one loop where you handle this macro scale, and you have another loop where you have these micro scale elements handled simultaneously. But basically, it's very easy to parallelize because you take one macro element, you put it on every processor, and you have another one waiting. As soon as the first one is done, the second one starts, and that's it. So if you do Newton method on each and every scale, you can have a quadratic convergence. Every iteration, you double the number of what you call it zeros behind the decimal point. Here 0, 10 to the minus 8, 10 to the minus 16. Here will be 0, 10 to the minus 7, 10 to the minus 21. You can see 7, 14 will be 21, even better than 22. After that, you can see by increasing the ratio between microscale and macroscale, I get homogenization bounds. The bigger is this ratio between those two, the more it's close upper and lower bound together. It's really like a what you call it, homogenization. Then if you want something else than Newton, Newton, of course, is the most costly, but is the most efficient, most robust. You can use Gauss-Seidel or Jacobi. These are kind of Fokker-like iterative methods, or BFGS. This is quasi-Newton method. One should be warned. Sometimes it doesn't converge. This is the case here, because one element was stiff, the other one was soft. And this will be represented if one element is failing, the other one is not. Then the failing element becomes soft, the other one is stiff. So you will get into trouble unless you have very robust solution method like Newton. And then after that, you have this, what do you call it, a two-phase material with plasticity, the one that failed with the Riegers and Zodi type of thing. So what was really the problem? Since you have two phases and crossing element, one is plastic, one is damage, the problem is the following. You can actually never have the stress field to be constant. Namely, if you take stress vector to be constant along the interface, that would imply that sigma nn and sigma nn plus and minus are the same, and shear stresses are the same. But if that's the case for the normal shear stresses, then the shear strain and normal strain cannot be the same. And you have to enrich the strain field correspondingly. And this is what was done here. I'm not going into details. These are just really details in order to capture the proper variation of the stress field. And then you go along. Now, if you really, if you do that, you get the perfect result, which is given here simply by using standard computation and this enhancement and you can have your perfect result at this level. Now, if you go into softening, all that I explained up to now is not enough. We have tried this, and you have a monoscale computation, you have a certain amount of softening here. Obviously, this one is not good enough because it becomes mesh dependent. It doesn't go down strong enough. Now, what you have to do, you have to include at the macro scale another variable which is representative of this crack. In other words, macro scale displacement are not only tied to the macro scale displacement in the corner, to standard interpolation, but also to this discontinuity. And then basically gives you another type of connection for the micro displacement and macro scale displacement on the boundary. And once you run that, you have a perfect match with the monoscale computation with all defined scale and this multi-scale computation with the software. Of course, that becomes a little more intensive parallel computation, but it's no big deal. You just have some extra variables to compute for every macroscale element and run it into this stuff here. So basically, this is how long it should go, for 1 hour or something like that. Is that good time to make a? Yeah, can we stop maybe for 10 minutes or something like that until we start again at 5:30 if it's okay. Okay, all right, guys. So relax. We start again at 5:30 and enjoy it, huh? Yeah, we can. After that, we can have questions and stuff like that. Okay, perfect. So we start again 5:30. I have here 5:20 sort of. Huh? Thank you so much. So I hope I have managed to teach you how we handle this modeling of fracture and structure level and material level. So basically, some benefit of one approach and the other approach, I really try to convey in what are the most important messages. Now would be the time to go to, again, using probability in all this business. So I call this section reduced order modeling or stochastic plasticity. And that's actually what we are supposed to get in this main message. So basically, the story goes as follows. If I'm now doing a true multiscale modeling of concrete, this, as I said, is something like a goal-dependent problem. Multiscale analysis is goal-dependent. What does that mean? Is basically, I want to be able to represent certain behavior of concrete. First, for the start, I'll say that the scale that I'm using to observe what concrete happened to be doing when you have a fraction failure is placed at the scale where I can clearly see the difference between aggregate, cement paste, interface transition zone, eventually voids, water, and all this complexity. After that, the goal of my modeling will not be to reproduce everything. What I'll be reproducing is basically the strain energy of concrete. I'll be reproducing the dissipation of concrete all the way to fracture. And that's really the kind of purpose. And then especially what I'll try to convey is the role of probability in all this. In other words, up to now, I have illustrated by this material level modeling only how this could be done, sort of two-scale modeling for three-point bending type of tests. But now what I want to illustrate is how you really do it in the three-dimensional world where you take into account all the possible, let's say, subtleties of approach that computations are supposed to be replaced or at least supplement the testing. And that's really the goal of my lecture there. So basically, if you want to get proper, now see your application, very good. If you want to get the proper interpretation of concrete, first of all, from 2D, let's say feasibility type of studies, you have to go to 3D studies. In other words, concrete is intrinsically three-dimensional material. Then we did this simplification where we took the proper aggregate sizes from small to big, but we turned them to be spherical because this simplifies a little bit preparation of geometry. Of course, true aggregates are not spherical, but we'll deal with that as we go along. We can make it as any size, any shape you want. It's really no big deal. And then this result here, when I switched, okay, I just started first, Patricia, with just saying that I'm going to be switching to 3D version and nothing else, and to do really probability type of approach to concrete. That's the idea. Did you want to announce something more or what? Did you want to announce something more or not? Okay, perfect. So basically the idea is really that I have started with saying that in this particular case, when we really have to tie this to the real life material, you have to do as good modeling of real life material as it is possible. So again, the concrete is done in 3-dimensional modeling. The aggregate size is taken from small to large according to this EMPA or Fuller curve that is used to build the concrete. And then the only simplification is aggregate is taken to be spherical, which is really, in my mind, no big deal. So what we show here is that monoscale computation or multiscale computation, when it comes to elastic analysis, you have perfect match. I also show that this perfect match goes into the hardening regime, into a softening regime. That means all these things are really verified. This has first happened in this paper in 2012 in Computers and Structures in collaboration with Herman Matisse and Pierre Villon, where there was a thesis of Martin Hautefeuille. Martin is now in the United States, so many of my good students either went to industry or went to abroad. So what the hell? You can never predict what is going to be a development of these guys. So the idea goes as follows. I can run this video, but since we had big problems, I need another presentation. I'm going to skip this video. It doesn't matter. Just to explain a little bit the ingredients. So here you see the typical representation microstructure that we had chosen. It is done in terms of so-called Voronoi cells. Basically, what you see here, first of all, the white colors are typical aggregates. It's like 2D picture of the 3-wheel world. Aggregate, again, are taken as spherical. And in white, these aggregates, in violet color is cement paste. In green is this interface transition zone. And basically in these dark bars, dark blue, let's say, bars are these cohesive links that are keeping Voronoi cells together. So at the microstructure level, we're going to be representing the failure modes, not by the finite elements this time around, but by Voronoi cell. Why? First, Voronoi cell is much faster to build the mesh. Secondly, this is one of these discrete models which will represent isotropic linear response. We are not after linear isotropic response, but in any case, we have to start with that because before becoming into hardening and fracture, you first have to be elastic, preferably isotropic and linear. And you can see that to prepare the data for such a model, we said that inclusion, that means aggregates, is simply elastic. Typically, it took 70 gigapascal to be modules of this inclusion. Then cement, you can be testing independently. Here we took that it has a much smaller, of course, value for Young's modules. It has a rupture at 2 megapascal. This is conditioning the traction resistance of concrete because you will see it breaks through cement. And secondly, the fracture energy of cement is taken to be 9 joule per square meter. Interface, we could go and we will do into the very elaborate modeling with random fields, but initially we can just take it to be deterministic. So what this model can do, first of all, is the following. From one realization to another, you move the aggregate to different locations because this is how you build concrete. You're doing a mixture, so aggregate goes a little bit to the left, a little bit to the right. But if you want to be comparing different computation with different realization, your mesh has to remain fixed. You cannot be changing the mesh. Otherwise, you will have an error in the mesh representation. So what is important is to keep these cohesive links from one realization to another to be the same and aggregate the white spheres, go left and right. So you end up having cohesive links, which are supposed to be modeling the fracture in 3 different locations. There's one which is completely in the aggregate. This one is considered to be elastic. It doesn't break. The one which is completely in cement, this one is elastoplastic, it can break. And the most interesting one is interface. Part which is in the violet color, it can break, and part which is in white color, it cannot break. So basically, you have to present this most complicated behavior. In other words, the one which is a little bit in aggregate, a little bit in cement. For this one, we introduce this jump that is supposed to be handling the breaking point. And from this one, we need also discontinuity of the strain field, because here, for the constant stress, you have 2 different materials. So strain has to have a jump, because simply you're dividing the same sigma here by E1 and here by E2, E1 being the Young's modules of aggregate, which is 7 times bigger than Young's modules of cement. So strain cannot possibly be the same. So when I do this, I have a so-called embedded discontinuity model, which has a representation of fracture given here, but it also have a representation of total strain field to handle the heterogeneous material that happen to be used in these cohesive links. Interestingly enough, I have 2 extra parameters, and I get, that was your question after the break, what is the difference from XM? So when I talked to Milan Irashek, a guy I know from DICE when I was at École Polytechnique Fédérale in Lausanne, he was convinced by late Ted Belichko, when Belichko visited Krag that his embedded discontinuity was not good because they stopped here with only one mode, and then they compare this against XM. XM is this interpolation. We have a standard shape function for the displacement field. Then you have a crack here, and then you multiply this Heaviside function either by N1, and you're handling this with the alpha extra parameter, which is sitting here, or by N2 times Heaviside, and you handle this with the alpha 2 parameter, which is sitting there. But you now have 2 parameters as opposed to 1 if I stop here. And this is not fair comparison. I said what is missing here is the second parameter, which is going to improve your strain field for the fact that you have a heterogeneous material. And now I know that this improvement here is actually extra global equation that I have to solve in operator split globally. And this one here is just a local equation that I have to solve in this internal loop like plastic variable. And I get remarkably much better result than XM, which is incapable of distinguishing in this alpha 1 and alpha 2, which part goes into inelastic and which part is correction of the elastic strain. So basically, I think this one we won. What this model can do is really remarkable. You cannot do this in testing. You do simple tension test, you show that 150,000, 300,000, 600,000, you start converging. You get really a failure in tension. You cannot even do this test because if you put a specimen in a testing machine in simple traction, you're going to squish it before you break it in tension. So basically, here it's recovered in 2 ways, the fracture, either in terms of these cohesive links which broke. You can see that typically you follow the interface between aggregate and cement because you have a stress concentration of the contact aggregate cement and they are breaking. So the fracture surface is never even. It really follows the whole process of the aggregate. If I pull in X or in Y or in Z direction, I get roughly, it's always one surface which breaks. So I get roughly isotropic behavior. For such a model, it's logical that concrete is isotropic material. And then basically the next one, if I now squish it in compression, it's basically the one with it has many links because of the Poisson's ratio effect. Many links are being broken. And so you can see that concrete becomes 10 times more resistant in compression than in tension. It's kind of normal because you get all these links there. If I do in biaxial compression, you get this typical failure pattern, okay, the links broken. And then in biaxial compression, you have it a little bit higher than uniaxial. So now I'm interested in getting the wealth of this microscale computation with the cohesive links at Voronoi cells replaced by a representative element at the macroscale. And so this element will be embedded discontinuity. So again, this is the typical failure surface potential failure. It is really following the interface between aggregate and cement. However, I'm going to replace this with a plane surface. So these are straight line rather than this jagged edges type of line. And so then I'm going to identify all the parameters of this embedded discontinuity element. And they happen to have this elastic response. This is bulk modules and shear modules. Then the traction resistance, compression resistance, fracture energy is traction, fracture energy is compression, and so on and so forth. So this will be done again by starting at the random field computation. In other words, I'm now taking that these interface properties are random fields. In other words, they change from one element to another. So you have a certain distribution at the level of X, that X is any position of one of these cohesive links. And you have for different realization omega. That's what random field is. So basically, if I go from X to another X, this will have a different resistance in mode 1. Tau U is mode 2, and tau V is, sorry, mode 2, and tau W is mode 3. And so basically, this could be characterized by covariance of these type of fields. And I'm going to assume that they are statistically, let's say, homogeneous, and they're characterized by correlation length. In other words, this is how long I have to travel to estimate that the Euro structure is roughly homogeneous. You can estimate this in a very nice way for concrete structures. For example, in France, we have a 35-hour working week. So whatever is produced in your structure from Monday to, say, Thursday morning, it's probably good. If it's produced on Thursday evening or Friday night, you know it's not good anymore. And so basically, you can see, follow the construction, how much you managed to construct from Monday to Thursday. That's what your correlation length should be. And that's how you can actually decide if you don't have any other means for that. So basically, then I need a macro scale embedded discontinuity element with all this extensive plasticity that can accommodate the wealth of the results at the microscale. So here I have introduced, of course, kinematics with discontinuity. And of course, you have a fracture process zone. So this one is handled with the 2 plasticity criteria. One of the so-called Sonvenan. We developed this by saying if you have principal elastic strain going over certain limit, it will break. Then you take the same criteria because you have three principal strains, epsilon 1, 2, and 3, and basically they go over a certain limit, they break. Of course, epsilon 1 is always bigger than epsilon 2, so admissible region really can be just half of this wedge. And then if you turn this into the stresses, you can build this in standard format of plasticity. This is your illustration of this criteria that can handle fracture in compression and fracture in tension, uniaxial tension and compression. Now, because if sigma 1 is a tension stress, this one will be breaking. If sigma, let's say this one will be breaking. If sigma 1 let's say sigma 2 is compression stress, epsilon 1 will be positive and it will be breaking because of the lateral type of it. So in the first case, crack is perpendicular to the loading direction. And in the compression test, crack is parallel to the loading direction. And you can really have a nice representation of the uniaxial tension and uniaxial compression. If you have a shear type of failure, you can handle this with Drucker-Prager, non-associated plasticity, where you need something like tangent phi in your plasticity criteria and tangent C in your, let's say, flow equation and so on and so forth. So combining these two, you have one part which is handled by the Saint-Venant and one part which is Drucker-Prager. And you have these parameters describing all this. When we published this in Computers and Structures, one of the knowledgeable reviewers wrote that, in fact, any of these ingredients in this paper is nothing new, but he never saw this or she never saw this combined in a single model. And you really need this to be able to represent the wealth of the phenomena that microscale model is capable of producing. As I said, these pictures for me are really impressive. You cannot produce this with monoscale. Simple tension test, axial, and then you have these isotropy, three-direction, compression, back compression. Everything looks so perfect, so realistic, basically. Arnold Platz got the job with Lapage as soon as you're able to produce this. So basically, the idea is now, how do we now identify? What I'm going to be identifying at the macro level will be simply a random variable for all these properties. And we already discussed that Markov chain Monte Carlo is not so efficient compared to polynomial chaos. So I'm going to be using this Kalman filter type of story. Basically, I'm going to be computing the strain energy at the microscale and comparing this against the strain energy at the macroscale. Or I'm going to be computing dissipation at the microscale and compare this against dissipation at the macroscale. And from that on, I'll get distribution of my parameters. These parameters, again, are bulk modulus, shear modulus, tensile and compressive strength, fracture energy, tension, compression, and so on and so forth. What you have to run are these standard tests, computation tests, either uniaxial compression or uniaxial tension. After that, you can identify this, as I discussed in detail, with the type of parameters that are bulk modulus, shear modulus, tensile, and so on and so forth, by using this Kalman-Markov filter and so on. And basically, here are some results. If you really go for the elastic response, you can go very narrow bounds. We already discussed this in homogenization. I'm going to skip this very quickly. You need standard testing with the shear and bulk and so on and so forth. Conking being aesthetically isotopic material, it allows you to do this in a very nice way. Now, if you go into compressive, the things get more complicated. You have to identify the yield stress, these two angles, phi and psi, which are featuring in the yield criteria and the flow equation. Then beta in the way how quickly you go to saturation and so on and so forth. And you can see that some of these parameters, they have cross correlation. That means you cannot be identifying one at a time like we did for elastic response. We identify shear from the shear type of specimen and for bulk modulus from bulk type of specimen. Here you have to have a sufficiently general loading program to be able to identify all this. But still it's possible. Hardening is no big deal. The biggest deal is softening. If you look what is the product of the identification of the variability or probability distribution of these softening parameters, you can see that they are very strongly non-Gaussian. So you can never hope to have a sensitivity to fracture to be Gaussian. It has to be specifically worked out in a specific microstructure and stuff like that. So now you really, you have a quantifying what can happen in the fracture in a very kind of a high way. Now I want to go to reinforced concrete because we had the highest level is not only concrete, but reinforced concrete. Now I will need not only concrete, but also reinforcement and of course bond slip. So what is the kind of modeling? Well, for concrete, you can go for this stress resultant modeling. This is what people do typically in this design. So stress resultant modeling, that means you take a reinforcement and you take a concrete together. And if it's bending, you produce kind of moment curvature diagram with these prominent values, where you have first cracking in concrete, when you have plasticity of steel, then ultimate value of behavior of concrete, and then you go into the softening. So you can go this test resultant. Of course, this will give you ultimate limit load of your reinforced concrete structure. You can do this computation in a more elegant way, where you put it into multi-layer or multi-fiber beam, and you compute this elastoplastic behavior for concrete, elastoplastic behavioral steel, and you do numerical integration of the cross section, you build the same stress resultant model, but numerical. Or you can do the model that I want to discuss a little bit more in detail, which gives you crack spacing and opening, which is the most important for the durability purpose. So what is this model about? First of all, I have to introduce the bond slip. That means connection between steel and concrete is done through the bond. Bond is handled with the simplest possible model you can imagine. This is more Coulomb. In other words, Drucker-Prager in 3D. And you have like a pressure versus the shear stress tau. And typically what you have is you go until a certain level where the bond resists. After that, it just starts sliding. So it's elastic, perfectly plastic. This is the simplest model for bond. You cannot imagine more simple than that. And then you can have an increase in bond because some of these lateral compression would increase. You have a friction effect, so the bar resists even better. So at the end, I'm taking this bond slip, I'm putting this into XFEM. So now this is your XFEM modeling of reinforced concrete. What happened here is that I have a standard finite element interpolation for concrete nodes. And then on top of that, I have this bond slip, which has to be parameterized as a continuous field along particular steel bar. Because between one end of the bar, where you have anchors, and the other end of the bar, you typically say these two anchor points will not be sliding, but all the others can be sliding. And they all have to be connected together. So it's a somewhat non-local model, but non-local in the sense that you know what is the length of your steel bar. So it's not like intrinsic some kind of length, but it's really, I put 2 meter bar, so it has to be sliding it for 2 meters. After that, it stops. There's no more bar. And this is it. So when I'm modeling this, I have a concrete nodes with the DC. Then I have bond slip, and typically for simplicity, I put bar along the line, along the one of the edges, not to make it complicated, you can put it anywhere you want. But the idea, then you have a bond slip and concrete together, and together they give you steel displacement behavior. So now when I'm computing this, there are 2 ways of computing. Either I'm going to be producing concrete versus steel parameters to be independent, or for what turned out to be better, I take concrete and bond slip parameters to be independent. And then steel is simply recovered as a bond slip plus concrete. So if you do this, you have a variational equation which says, I move the concrete nodes, and with that, I move also slip. I also move steel nodes with the slip being fixed. And then I have an extra equation which gives me the remaining motion of the steel, which is introduced now with the bond slip at n plus 1. You see, here is bond slip at n, here is the bond slip at n plus 1. So this is like a plasticity that goes along the particular steel bar, which is now non-local, which I'm again computing the operator split. Of course, this relative parameterization is much better because number of iteration is much smaller than if you have steel and concrete, because it's natural. If you start having a concrete crack, then steel starts moving with this concrete which crack. And here you don't take this into account computation. But if you take relative parameterization, you do take into account when the concrete cracks and moves, then the steel will move with it for the fixed slip. And then you correct the slip and so on and so forth. So basically, what we have done is here, you have to do this, again, this is representation. This is your concrete element, and then there's a bond slip, and then steel is there, glued to the concrete. You can see these are the results of the 4-point bending test. In color here, you have a fracture process zone. What happens here, the moment is a constant in the middle between two solid forces, then gravity is linear. So cracks, macro cracks are these little red lines. They are vertical because it's bending dominated. And here, what is shear dominated, because the shear is dominant, they are inclined. So it gets really perfect prediction. Here, if you have a small, weak reinforcement, strong reinforcement, every crack is no big deal because reinforcement is dominant resistance. If you have a weak reinforcement, every Imperial, he was in this road and bridges type of laboratory, and he was using arc length computation. He was concrete. That means you have to be able to follow these jumps up and down. You cannot do with standard incremental analysis. You have to have a better solution procedure like arc length and things like that. So basically, this is the type of solution. You start with the prediction of the concrete and bond slip at time Tn. Then you go for the best approximation of what you have in terms of your concrete. Then you get corresponding bond slip redistribution because the concrete moved. And then you go back for the given converged value of bond slip. You compute again new correction for concrete, and you go from one to another operator split phase to be able to carry out this computation. What we discovered here, we can really get experimental results perfectly match without any cheating. There was actually the work which was done for Electricité de France, a colleague of mine from École Polytechnique, Professor Bruchwiller. He had 3 of these big bars with a big testing machine, and he had this crack spacing test where he pulls on the steel and the concrete which cannot follow start breaking. So he got experimentally 3 cracks, and you can have force displacement diagram for these 3 cracks. And then he also measured the opening of these 3 cracks. So without anything else but making sure that first crack would happen where he observed the first crack, you get these 3 cracks, and we have this opening of 3 cracks. You can see very interesting phenomena. When the second crack starts opening, the first one closes a little bit. And when the third crack starts opening, the first 2 start closing a little bit. That's because of this redistribution. This was the first crack that opened. You can see that basically this one is a sliding that occurred there. And then the second opened, the first one started closing a little bit. Then the third opened, then the first 2 are starting closing a little bit, and so on. You can see that it goes from concrete to steel, and it goes back to concrete, which is non-damaged very quickly. But it's really important to be able to handle this bond slip distribution in order to be able to capture the crack spacing and opening. And this was all done in deterministic manner. Now, if you want to be honest, you can say, well, bond slip is not standard. And you had this thesis result from Lyon, the guy called Dowd in 2003. He had tested many of these specimens. You see the steel bar is booming out, and then he observed the cracks. So every specimen has different redistribution of this crack spacing, and then of course opening follows. So we took the one of these specimens which says the cracks are from 14 to 19, and then we did this. That was a thesis of a student of mine, Norberto Dominguez. He's now a professor at the IPN. He's the biggest engineering school in Mexico, even the head of research. And so basically, we tested first when you don't have bond slip. Of course, it's not good when you have bond slip, but uniform is not good either. But it's enough to have a 5% variation of bond slip. This was done kind of ad hoc, building it just 5% variation, and you get computationally 13 to 19 as opposed to 14 to 19. Then with the current thesis, which is being completed with Simona Di Brulla, being coached by Herman Matisse and myself, we did even more extensive computational results and being able to compare against these true results. And we're doing this now with Bayesian update. What we discovered basically is that you have to have a really very extensive measurements, because these bond slip type of parameters have to be occurring at the end. You first go through the cracking on concrete, then you need whatever moving the slip, and at the end finally you have this redistribution. So you need in this incremental procedure based on inference, you have to be running these results for a long time if you get meaningful measurements, or measurements are really computations for deciding the crack spacing and opening. But in any case, I think we have it perfectly under control. It took lots of really all these discrete approximation to get there to say what will be the crack spacing and opening. Now I want to discuss some of these simplified interpretation type of ideas. What is really the size effect? So up to now, I have been presenting the reduced model in terms of random variable. You'll see the key idea for the size effect is I'll be representing this reduced model in terms of random field. Let me first recall what the size effect was. When you do the testing in 3-point bending test, you have a heterogeneous stress field, heterogeneous material. It happens that the size of the specimen will start changing the dominant failure mode. If the structure is small, according to Bajant interpretation, I don't know what small is, but anyway, I'm sure he does. Basically, you get continuum mechanics type of failure. If the structure is large, you get linear fracture mechanics failure. We'd have one crack. So we try to do better. One actually of these papers is the honor of the birthday of Patricia in this international journal for multiscale computation engineering. Hopefully, it will be coming soon. In any case, this is what we've done. We took aggregates, again, our spherical aggregates, distributed into the sphere. These are strain energy type of results. And we now start to treat this probabilistically by using more and more measurements and basically getting better and better bounds. We compare this, what you see here is 5 and 95% of the probability of distribution. And you compare this with respect to the upper and lower bound, Royce as opposed to Voigt. This is Voigt, this is Royce. Or Hashim-Strickman is a better type of bound when you have so-called autocoherent. This is self-consistent model, which get more sharp bounds and stuff like that. And you can see we get better and better. In fact, what you really wanted to compute is the following. You spread your aggregates throughout the domain. You make sure that they don't overlap. So we did it with the Poisson process, but when you don't overlap, it's called Gibbs process. Then you fill in the corresponding number of small and what you call large aggregate. We take the behavior of the cement base to be elastic, perfectly plastic. So it means the first limit stress will be that the first cement element will be plastifying. Then you have a percolation because it starts passing through the thickness. So when you get percolation, this is your ultimate stress. After that, we don't compute, we call this ultimate stress. So you get many realization, and this realization allows you to build the corresponding distribution. So what this distribution is, we want to build a random field. In other words, this is your bar. If the properties are deterministic, they're just constant. If the properties are random variable, that means they have a same distribution whatever is the point x between 0 and L being the length of this bar. So this is very simple. That means every cross section has the same, but not necessarily. If you have now lots of defects in your bar and you have non-proportional linear program, then every section can have its own probability distribution. And this probability distribution decided by the random field, which is function of x, the length along the bar from 0 to L, and omega being realization. So isotropic correlated field characterized in terms of correlation length. Again, this is the distance that you have to travel to find the properties to be roughly distributed in the same way. And basically, this is what is spelled out in this way. So as I said, correlation length can be established if you know how you build your structure. If you have done the same work conditions and stuff like that, it's likely to be homogeneous. If there's something changing, it's likely to have a little bit more difficulty. So basically, what do you now compute? You take 3 bars, one which is the same length as correlation length, what means that bar is very likely to be homogeneous. Then you take some medium bar, which is 10 times bigger, and you take large bar, which is 100 times bigger. And you take this realization of this properties of this bar in terms of the yield stress, in terms of the gap between the fracture stress and the yield stress, because we wanted to have positive values, so we need this gap all the time. Because ultimate stress should be bigger than yield stress. Otherwise, with this random stuff, you can actually have fracture stress smaller than yield stress, and then you get into trouble computation. That's why we, instead of parameterizing sigma y, sigma f, which is fracture stress, we parameterize sigma y, yield stress, when you start giving fracture process zone, and then difference between fracture stress and the yield stress, so that difference is always positive because you take log normal. And so you can see that very large bar is the most heterogeneous, which is normal because you're 100 times bigger than the correlation length. So after that, we run these computations, as I described, for coupled mechanics probability, and we start putting 10%, whatever, 30%, and so on bars that are broken. And you can see, first of all, that the short bar will be breaking at a higher level because it is most resistant. And secondly, the type of diagrams here that are really very much characterized by the length with respect to the correlation length start looking very much like what Bajan was advocating. The only difference here, I know what I'm talking about because I have a correlation length of random field characterizing my macro scale properties. I have a microstructure, I have all these computational effects under control. And so this is very similar to what is used in this business and known as a Weibull, so-called weakest link type of thing. Only here we are just one step better. In other words, Weibull has only one weakest link, and that's it. Where here we have a fracture process zone, and we have this softening. And so it all depends whether you're going to be dominant by the fracture process zone, if it's homogeneous short specimen or very large specimen, where you not only fracture will occur first, but contribution fracture process zone will be the smallest. Then I also wanted to comment very briefly on so-called what I call scale effect. Now, this is dynamics. Normally, if you study dynamics in your life, you normally have a very interesting result that dynamic equation, if you want to take into account the damping, most often in structural analysis are described by using so-called Rayleigh damping. So Rayleigh damping is you have mass times acceleration plus stiffness times displacement, and supplemented on top of that, damping matrix times the velocity. It should be just one dot here, sorry about that. And so damping matrix is linear combination of the mass matrix and stiffness matrix. Or you can quantify this in terms of so-called damping coefficient, which could be computed from the given frequency and the value of these parameters A0, A1. So a typical diagram goes as follows. This is your damping ratio with respect to the chosen frequency interval. Those damping that is proportional to the stiffness, it goes up linearly, and those which is proportional to the mass goes down in terms of some kind of hyperbolic type of function. So basically, combine these two, you can have some kind of desired value of damping only for the given values of the frequency, but nowhere else. So this is the first problem. Second problem, really, what we are trying to compute is not that. We are trying to compute typical answer to earthquake. So in earthquake, you have a first slow shaking, then you have a strong shaking, where you need all this plasticity damage. Then you have a free vibration of a damaged structure, which is not the same as a small vibration under viscosity. And then you have to take into account all sources of damping, really. If you take a complicated structure, you have sources which are related to the damage of concrete, reinforced concrete that I just described. You have the sources that are radiation damping with soil. You have the sources which are resistance of connections and all kind of stuff. So the only thing which is good about Rayleigh damping is the fact that it matches experimentally observed results. If you start vibration and you measure the amplitude, after some time, it will start decaying in the exponential manner. And this is why people took exponential type of manner to put Rayleigh damping. But if you change the size of the structure, you have to repeat the test again, because Rayleigh damping is computed from the given mass and given stiffness. So you have not only material, you have the size of the structure. And so your measurement, typically they say 5% for concrete, 2% for steel. How the hell you get your 5%, 2%? If you want to look into that, it's not going to match. If you match one of these intervals, the others will be fair. So what we did is the following. We introduced this into multi-scale modeling of beam. So here, microscale beam, which is nice and homogeneous. And then fine scale beam is simply your multi-fiber beam in 3D. Some of them could be concrete, some of them could be steel. Well, to keep it simple, we did this. So basically, you have your experimental measurement. Typical, let's say, concrete compression test in dynamics would be this. You can see that concrete has both change of the elastic response, that means you need something like damage, and you need a residual deformation, which is typically brought by plasticity. So we matched this by coupled damage plasticity model in a paper which came out this year in coupled system mechanics with Rosa della Mea Nava, postdoc of mine now. And basically the idea is that what we matched is not this beautiful shape of this kind of, what do you call it, like eggplant hysteresis loops that are really measured experimentally. We just tried to get the same surface inside of each of these hysteresis loops. And this one, which is done linearly, the surface inside is the same. In other words, dissipation in the typical hysteresis loops remains the same. And why is it important that we took linear? Well, because now linear hardening, linear softening doesn't need any iteration. It's one computation, it's done. So our computational model goes as follows. At the macro scale, I'm computing these equations of motion. These are here, these equations. At the fine scale, I'm computing this damage plasticity for each and every fiber. And so this is summarized here. This is the computation for this linear hardening, linear softening, coupled damage plasticity for each and every fiber. That means as many fibers, as many of these equations to solve. It looks like a lot, but they're linear. So it's just one iteration, they're done. And then this is global scale computation. This is beam bending problem. So I have a typical inertia effect. These are the stresses that influence fiber by fiber. So I'm simply summing up of all these fibers multiplied by the cross section of the fiber, and this is it. Now I'm doing this in the hybrid stress type of formulation. In other words, I have interpolation of the displacement as opposed to interpolation of the stresses. That allows me to compute my tangent stiffness in a very efficient manner, because all these inelastic dissipation mechanisms are now supposed to be additively adding. And I first compute the inverse of elastoplastic tangent stiffness, damage tangent stiffness, and then sum up all these contributions, and then invert, and I get my stiffness which I need for the next global step, and so on and so forth. So this is, although it's much more elaborate, it is a very efficient type of approach, and this gives you a type of thing that you cannot dream of about having with the real type of thing. So what does that give you as the final result? We then put contribution of the probability. And again, the key point is using the random field. So random field of these yield stress, that every fiber might have a different yield stress. And so this being a random variable, given that the fibers are in the pure bending and the stress is linear across the thickness of the beam, that becomes something like a random field of representation of this yield of the fibers throughout the section. And so what we did is we played with the standard deviation of these yield stress distribution as a Gauss normal function. So if you keep a very small standard variation, that means structure is going to be very likely very homogeneous. You almost have deterministic value for each and every fiber. So basically you get something which is linear decay of the amplitude. And this was well known by Inman, who wrote a nice book on that. When you have a friction to be a dissipative term, not Rayleigh, which is a velocity proportional, you start having not an exponential decay, but you have a linear decay, and you can compute these results analytically. But if you now have a large standard deviation, that means structure is very heterogeneous because it's very large. So you have a weak fibers and strong fibers. Now you can see that your decay for the large standard deviation, this one is 0.001, and this one is 100 times bigger. So basically, you start having exponential decay. And so you really get corresponding global solution correct. And you don't have to change anything because this is characterizing your material level. So you're using the same fibers to build any size of the structure. It's just the distribution of these things, how they have to be there. So this actually brings me to the conclusions and stuff. So we have time to discuss. Let me first go through the conclusion and we go into discussions nicely. First of all is what I really try to convey here is these different type of ingredients of the model for handling the fracture in terms of the size effect and the reduced model. So what I find really the main novelties is first of all theoretical formulation, which is very strongly rooted in thermodynamics. We just don't need any regularization, any intrinsic length or any type of viscosity or any type of trick like that. You simply need one of the most reliable parameters to identify, and this is your fracture energy. GF is the energy that takes to go load the structure to ultimate value and then tear it apart that you have to put the glue to put it back. So every material has a fracture energy from paper to human being, if you want. So basically, another ingredient was that we chose discrete approximation, which is adapted to each and every scale. So basically, at the microscale, those were your voxels. This is modeling of the cement. At the mesoscale, those are your Voronoi cells. At the macro scale, this is embedded discontinuity finite element. At the XM macro scale, this is reinforced concrete with the XM representation. So if you look into literature on discrete approximation, you will find that this covers all set of discrete approximation. I didn't think there's no more, if you want to think of that. And basically, we kind of use each and every one to be playing appropriate role. And so after that, we came up with rather than homogenization, we came up with the notion of stochastic upscaling. That can, of course, recover homogenization if it's possible, like for elastic properties, but that can actually replace if it's not appropriate, like for the fracture, XM, and so on forth. So especially when the scales are not separated, then of course you need to replace these things in a better way. And then finally, if you want this type of models, they have a behavior that goes way beyond what traditional models can do. They can give you crack spacing, crack opening, crack propagation, size effect, probability-based durability estimates, and so on. Now, for me, the way we were building these models, it brings back this issue today's artificial versus what I call natural intelligence. What we as engineers who have a knowledge, this goes back to thousands of years, because if you talk about durability, Rome knew how to construct the structures that are durable for more than 2,000 years. This is called Colosseum. Of course, this could have been constructed only by emperors who had money to construct such a structure. Today, there are many more clients who want to have durable structures, and they cannot all pay this kind of money that emperor was able to pay. So this was us engineers entered to kind of help them out constructing the durable structures with the smaller money, with the probability and good modeling and so on. Also for artificial intelligence, nowadays you have a big hoopla about, because these young guys who built Google and Facebook, they made billions, and they are still guys in 30s and 40s. Well, they were lucky enough to have internet, which was built to fight the nuclear war against Russia, not really for their applications, but they happen to be lucky building that. And if you really think of building a model on top of the stochastical type of, because this is what happened to crisis 2008. French mathematicians, the best of them work for banks in New York and London, and they could not estimate probability how much people start fearing when the value of their homes goes down. And there was a big crisis that happened in 2008. In other words, if you just have statistics without really knowledge of what you're talking about, you cannot go very far. So in my mind, statistics cannot replace modeling. It cannot replace natural intelligence, but it can certainly help a lot to enrich modeling and to get the bounds that you're really trying to get. Then at the end, my motivation for that comes from the cement and concrete type of composites, and the big client, which was called the Électricité de France. Of course, we had to handle very complicated problem, which is unique and not so highly valued, because it's not typical nano world that was king before this life sciences, which is currently the king in research. But it has tremendous complexity, because at the level of microscale, you have 16-phase representation. So you cannot even represent that in the deterministic way. It has to be probability from the start. Then certification validation. Many industry people used to believe only in the testing. But it so happens that very large structure you cannot be testing. So this is now the philosophy, how you replace testing by using a fine scale, lots of material tests combined with the probability and computation. Finally, you can go into many other application domains. all the ingredients of my reinforced concrete modeling, starting from fine scale to the larger scale, directly applied to modeling what we are doing right now. And this is this carbon fiber reinforced polymers. You also have very large fibers. You also have matrix. You also have whatever fracture process and so on and so forth. What are they used for? Well, they're used nowadays for the application that are called large wind turbines, because there's a push to deliver a 10 megawatt wind turbine, let's say, facility in Europe. The largest one goes to 50 megawatt. And so happens with quick computation, say 2/3 of the energy of a wind goes into the producing the energy. You can very quickly recover that you need 100-meter blade. So 100-meter blade to get there, you know, in French you say bonjour le dégâts. It's very difficult. You really have to do, you cannot be testing that. You have to do the same recipe like I did here, testing at fine scale and go to the large scale to get this corresponding stuff. So we actually have some results there, especially the key point is keeping the blades flexible. Since I'm using PowerPoint, I'm not using PowerPoint, I cannot run this movie, but this is currently dominant system produced in Denmark and Germany where the blades are stiff. So you cannot use this system really in the places where you need the flexible blades whatsoever. Then the ultimate challenge, the guys who have the biggest amount of money, we can also help them. With the health problems that you have, you realize that doctors know very little unless they already had experience with what happened to somebody new. Their all decision is based on experience, not really modeling, not really conceptual thing. This was actually spelled out by one of these guys, Dr. Lauer from National Health Institute in the US. He said, our ability to get imaging, you know, you have a scan of your stomach, you have a scan of your lungs, you have whatever, some other intrusive measurements to see about your health, from blood tests to whatever it is. But after you get all these measurements, they said our ability to understand what the hell is going on. You have now 3D images of your blood flow through veins, and you can now look at what it's going to be like if you have this bypass or that bypass. But is it really going to be like that? Nobody knows, because every human being body is very different. Somebody had a strong left leg, somebody has a strong right leg, and you cannot do these statistics unless you really go through that. So basically, I think potential contribution to the world of the most complex system, other than concrete reinforced polymers, but human body, are really humongous. And this is really the kind of thing that hopefully one day will happen. Actually, my former colleague from Kashan, a friend of mine also, Pierre Ladez, who was director when I was vice director. So whenever we finished arguing about who gets the jobs, who gets the new positions and stuff, then we would talk about science. My favorite times in Kashan was the lunches with Ladez, where everybody else was in cafeteria, and we had our sandwich, and he had these better quality meals. So he taught me mechanics, he's in French, la mécanique des solides suit l'évolution de l'informatique, hein, suivi une véritable révolution. La modélisation simulation est au centre. Au niveau industriel, la virtuelle est partout dans le bureau d'études et le calcul. J'ai coutume de dire que la mécanique est devenue la science de la modélisation et à ce titre franchit sans état d'âme, sans frontières d'un temps. In other words, mechanics, solid mechanics follow the evolution of informatics, just like artificial intelligence, and now is living the real revolution. And modeling and simulation is in the center of this. In the industrial world, and Ladez had the chair of Airbus, the biggest company, is really virtual, is everywhere in these design offices and computation. And he said, I had to say that mechanics and modeling science is now bypass the frontiers of other type. And I think he's fully right. So what you need is a verification, validation, coupling, interaction problem, mechanics and probability, model reduction. All these are tools for decision making to help these guys to say whether they operate and where and stuff. Because once they cut you, what the hell, they cannot come back. You know, so basically, before you start doing these very tough things, you better know what you're doing. So basically, this is roughly good news and bad news. Good news, there are many things to do. Bad news, engineers are supposed to save the world, because not doctors will do, not the other guys, mathematicians will do. Engineers have to step in. And actually, when I learned this, when I was a member of these panels, I was first 3 times member of the panel for consolidation grant. I saw the cream, the best young researchers in Europe, many of them Italians. Unfortunately, I would say many of them are not working in Italy. They were at Oxford, they were in Delft, and so on and so forth. But what the hell, later on, they come to Italy. One guy who got a consolidation grant because I voted for him, he was in Delft, now he's in Bologna. He knows who I'm talking about. So anyway, so basically, when I became member of this consolidation panel, I was jealous because when you look, there are 10 panels. Europe gave 45% of money. These are very big projects. You talk about 2 million for young person. 2 million is a lot of money. So basically, they got 44% for physics and engineering. If you look into panels, first is mathematics, second one is whatever physics, third one is chemistry. So all these pure sciences. And I was also a member of Synergy Grant. I really see these pure scientists, they are really what they call in French, grand recamblant. They really pump up importance of their domain beyond what is really important. Engineers are like little guys, but in reality, they have a luxury to be in their own small bracket, a little bit like doctors. Engineers, they have to face the real world. And then they put us in this panel 8. And if you look what they actually put together, judging the projects from the standpoint of aerospace engineering, chemical engineering, civil engineering, computation engineering, fluid mechanics, energy system, micro, mechanical, material science, production technology, product design, sustainable design, lightweight structure, industrial, you stand all the engineering together. For them, this is like composite material. Yeah. And maybe they are a little bit insulting to engineers, but maybe they're not wrong. At the end, somebody has to come up with very complex solutions. And the only guys who did that is engineers. Because why we live so comfortably, much better than the Rome used to be 2,000 years ago. Because we have a clean running water, we have electricity, we have internet, we have all the kind of stuff. Much more than Rome used to have, although they were like the top of civilization at that time. Thanks to engineers. Did we sell this in good money? No. The other guys that got much better money. So hopefully you guys will be correcting this much better. Now, I understand my lecture was very fast. I saw Patricia this morning putting the books. I said, well, they'll put my books as well. Take a picture, you have now phones. And you can actually buy this. I get only 10%. If I want to become rich, you have to start buying the books anyway. So the idea is really, there's a bunch of these books on different topics, and we have some more books. This will eventually come as we go along. So basically, I hope I got this right because I had Google translation. When I want to say thank you for attention in Italian, I say grazie per l'attenzione, like that. And if you're interested in some of these things, I do have money, and I might have some more money because this year I got projects. I was surprised how many I got. So contact me, very easy to Google me, either adnan.ibrahimbegovic@utc.fr, or this is my homepage. If you click, you're going to go there in a jiffy. And so this is what I wanted to say for here, and we have some time for discussions and questions. So we might as well do that. Okay. So I hope you're still there. Say something. Anybody?
Thank you, Professor, for the great lecture.
Okay, at least there's one person who said something. This is great. At least one person kept the, you know, there's a joke. They say the best students could not dream. They could not dream about this own platform. Let's say because now you can turn off Professor remote control. I mean, this is really dream come true. You're bored. You just take remote control, say off. Fantastic, you know. Anyway, okay. So now let us go for that. For the questions and answers.
Okay, first of all, I wish to thank you again for your general lecture. No, it's not.
You can come here if you want.
The general lecture, and which accounts for many topics concerning multiscale modeling and
that's okay. Doesn't matter. I mean, well, okay. They will see her now. Now we'll see her. Okay. You can just take a chair. You can. Yeah, no, you can.
Oh, sorry. Concerning multiscale computations and continuum mechanics aspects. And computer, it's a very wide overview on and also detailed on different approaches. And I think that is very useful for the PhD students to know a framework in which the speakers talk a different language, but on similar topics. So there are many points of view that can interact, and I do hope that our PhD students can find the occasion to interact, and maybe why not come by your university and share a time and period during the preparation of the PhD thesis.
With great pleasure. In fact,
Of
if you
course,
want
my interest, as you could understand this morning, is to find the possibility of using non-standard continuum mechanics for modeling of different approaches. But you are in the, how do you say, in the center of the homogenization school in the world, the most important homogenization school in the world, and I think that the possibility to interact with your staff in your university would be very useful. And this is just to thanks you again. And I do wish to invite our audience, the PhD students that are at home and connected by remote, to ask for some questions and keep this very special occasion.
Just one comment, Patricia. I didn't put the names of visiting professors. That's a mistake, but I put many of these current PhD students and former PhD students. These are recent pictures. This is from this year, end of June, early July. All of these guys that you see are either my current or former PhD students.
Marco can show,
and here's
also show the
list of these guys.
Our PhD student staff.
But anyway, it will be really a pleasure because, as I said, I had many PhD students from all over the world, but somehow not Italians. I don't know. These Italians, they typically stay in Italy or they go to Germany or whatever it is, to Dutch and stuff like that. Maybe they are more smart because at the end, they make more money. God knows what is the first criteria. But in any case, this will really be a big pleasure in a sense that you can organize that. One of the reasons. Yes.
Marco, would you ask the questions that already?
And you can also. Okay, let me stop sharing. Oops. Okay, share screen. Okay, but it doesn't matter. If you have any questions, go ahead. I try to open chat to see if anybody's tried to have a question by chat, or you can maybe say something. Turn on your microphone and ask a question if you want. Or here is some kind of in the concrete 3D model. Let me say, thank you. I'm in class. Okay, in concrete 3D modeling, I suppose the only one cementous material has been considered. Would it be possible to consider also cement plus CGBS or silica fume in some percentage? I think you can consider whatever you want, as long as you have kind of probability on quantifying what is the participation of this thing. So for us, we kept it the simplest possible level, which is you have an aggregate, what is called the distribution curve, which is either called M-Power Fuller. When I studied this thing, maybe they changed since that time, which says how many big, how many small, and so on aggregate. There's an interesting point. We were working, one of my former PhD students, he did PhD on this high performance concrete. In that one, you take this special French recipe produced at the time first by Bouygues, and it was called PR because the guy invented called Pierre Richard. So what they did, they reduced the water cement ratio. So what happened there, all the cement was hydrated. And then basically they get the increased compressive strength. However, getting increased compressive strength, it turned out that they get reduced tensile strength because this is actually all the cement being hydrated is not very good. And even worse, they reduced durability. So then they started putting the fibers, short fibers, 16 millimeter with a diameter of 0.1. And nobody ever explained why they only put 16 millimeter 0.1, because this is the guy who invented this. And then my former student became a boss for this, and he came for a seminar half a year later, and he said the biggest problem is to get these fibers to be distributed correctly. So we're testing this, and we had like a cross type of specimen. We're pulling it in tension, and one of the favorite results that I was showing to visitors of LMT Kashan was when now this specimen broke, and it broke at the place where there was not a single fiber in tension. It says this shows the result when you don't put the fiber, you break in tension. But you know, because it said you cannot orient the fibers you want. When you mix it into the concrete specimen, there's something called beton autoplaçant, self-placing concrete, because it's very expensive to produce it. So they put these adjuvants, like you talk about, they put these fibers, and then they put it like, you know, it goes into the itself by the gravity. But the problem, the final result is very difficult to guarantee. So today, this is very similar to something called additive manufacturing, because people talk with lots of excitement about producing whatever, any size, any shape of the structure by simply printing it in 3D printer, but they don't say what is the quality of this product, because often you're not really able to guarantee that the quality is as high as you want. So basically, this is it. You know, you can start with any kind of microstructure. Anyway, it's already complicated enough. It started with 16-phase product of this NIST cement radiation product, and then you kind of go into that and you produce durability quantification. I couldn't show because some of it is confidential, but basically whatever I could show, I did. So basically the idea is you can get quantifying the durability of this nuclear power plants and so on and so forth, but the idea is really you have to have a credible probability distribution of what you're trying to do. And then computation will do the rest. So there's no limit to complexity. Of course, if you have computation power, money, and good client who can pay you for that. Because this is work I presented that took me from 99 to 2014. This is 15 years of work in many, many clever people worked in that. And then we switched to many other things which are now currently paying better. So that's why I was saying, you know, if this ERC projects and things like already 4 projects, I have now 4 PhD theses, but mostly I have good candidates. So these are almost gone, but there'll be more funding basically. So God knows, if you're interested, contact me. And if you have a CV, either if you know Professor Travalushi here, or if you are really top student of your school, those are 2 categories I'm interested in. I have to have a colleague of mine, a friend of mine who can say, okay, this is a good candidate, or I have to have somebody who says I'm the top candidate by itself. This is how normally you get to me. Very easy. Do we need some more? Although most of the concepts were new to me, I really enjoy your presentation. Of course, your sense of humor. Well, I maybe switched the job because these comedians are paid much more than professors. You know, I was really jealous. Recently, I read an article of a lady who is the president of my former university. Now it's called Paris-Saclay. It's called normal Paris-Saclay, used to be Kashan and so on. She said we hired recently Leo Messi at the age of 34, probably has only 1-2 years to play at top level. And they paid him with the kind of money he gets and taxes which are very high. He's paid 70 million euros a year. And she says this is like 1,000 times the highest salary you can possibly have as a French university system. So one Leo Messi worth more than 1,000 future Nobel Prizes. Did he get something wrong? Did he have to explain to these guys from Qatar they could have invested in science in Europe? They could get even more benefits at the end, you know, rather than just paying for soccer. Yeah, basically. Would it work or not? What do you think? Huh? Yeah. No, but at the end, you know, I recently had a little bit tough problem that put me into intensive care. So I was talking to these guys in intensive care, and I said, what you're doing is fantastic work. And basically these rich guys from countries I'm not going to name, they could have paid you a huge amount of money rather than building PSG, Paris Saint-Germain football team. Neymar was bought for 200 million. Messi now is for I don't know how many billions. They could have bought excellent centers of medical production, and they're old. Typically, all these rich guys are very old. They can come to their private facilities to be cured their health rather than watching a soccer game. what the hell, you can watch soccer game anyway. So this is really the question of priorities. I don't know what the hell they think, but typically, you know, my last name, Ibrahimbegovic, that comes from the times when Turkey was the 500 years dominant power in Balkans. And so Bosnia was a zone turned towards, let's say, Western Europe. So if you are loyal to Turks, you get beg. Beg is like a noble title. It's like tu quelque chose or fon quelque chose. So my father was a double beg. Ibrahimbegovic, Ismail Begovic, 2 times beg. And my mother was a very modest origin, good in math. So although my father was first, who was not really rich, as the family used to be rich. And basically, these rich guys were not very educated. So their decisions are not really decisions that estimate the science, you know, basically. That's really the problem most of the time. It really takes, you know, wealth is not connected necessarily with the, it could be connected much more with the good luck than really with the great intelligence. Now, the progress, as I said, you know, that we live much better today in Rome than Romans, who were the richest guys at that time on the planet, on the civilized planet, lived. Obviously, that's thanks to these guys like us, not like the guys who played soccer. I'm sure they played soccer before. They called the gladiators. They kept the head and they start playing soccer. That didn't change too much, really. Rather, it's called the modern gladiators, really. So it used to be Romans were clever. They paid gladiators nothing, you know, piece of food, you know, and the other guys were paid more. We paid gladiators much more. What can you do? Maybe I should run for president in some country to change these bills. This would be kind of the idea, anyway. But this is another joke, anyway. Oh, can I also read one more question here? I have been tasked with the modeling of masonry walls for my thesis. I've noticed other papers references continuum mechanics, but was never introduced to the field before. It seems interesting, but I'm puzzled as to how this would apply at the larger scale than concrete impurities discussed here. So I can actually share again my screen showing you the this page here. This was the only computation that I put there for masonry, and it has all the concepts. This is it. Yeah. So this is your multi-scale modeling of masonry. And basically we introduced the failure modes for brick, failure mode for the interface, and this is the kind of results that multi-scale analysis gave us. Compared to experimental results, which is here, we could really now Bayesian inference improve this result much better. Of course, I already mentioned, it has to be now, you know, probability distribution is good if you really have production under control. So if each and every brick is modern brick, which is produced in a reliable factory, which is in France, they are 50 centimeters long, 20 centimeters high, 20 centimeters thick, and you have a similar quality, you can hope that your probability distribution will be good. If you take the structures that were built in Roman Empire 2,000 years ago, then probability distribution might be a little bit more tricky because you never know which part of stone comes from which neighborhood where a Roman emperor was doing. So really, all key point, if you really want to make sense of probability, you have to be able to master the probability distribution. Otherwise, probability cannot replace modeling. It will simply give something what we call garbage in, garbage out. In other words, you have a wrong probability distribution, your results, whatever you do with the equations, will be wrong. So you have to have a good model to have transition of these scales, and you have to have a good probability distribution to know what you're talking about. So concrete and reinforced polymers are really good structures because they are built in one shot. If you take steel structures, they are built with the connections. So you have these prefabricated steel profiles, which have a perfect quality, or used to have perfect quality before we had Arcelor, but then with metal, supposedly it's not the same quality, but nonetheless, let's say they have perfect quality. And now it's not that, but it's actually connection. In steel structures, most of the failure comes from the connection. The connections are either welded or whatever, bolted and stuff like that. So it all depends on this guy who is welding it or this girl who is welding it. On Monday, they're in great form, they do a good job. On Friday, they are rushing to go and do a weekend. So you don't know which connection was built on Monday, which was on Friday. So this actually becomes very complicated to follow. So anyway, that's one of these things that hopefully can help you. Masonry definitely could work as long as you know how to build your probability distribution.
What about failure of mortar?
It could be the same way, you know. the mortar is in a way you want to do it. It's interface really. For me, since the interest was concrete and then reinforced concrete, mortar was mostly like reduced to interface type of thing. But you can go further down the road, and some people are interested in this type of fine scale type of things. In fact, this NIST model, first time I saw it, I didn't know what it was. I learned this from a lady called Michelin Moravin. When she came to Kashan, she was already retired. She was top expert on physical chemistry. She was not an engineer. So she showed me this. I said, Michelin, what is this? She said, this is NIST product, 16 different phases at the level of 100 micron. I said, can it be 2 or 3? And she said, no, they're all beautiful. I don't want to give up any of them because I wanted to reduce to something more simple. I said, no, 16 is really like minimum. I said, okay, let's do 16. Okay. Yes.
May I just add answer to this question? I want to focus on the fact that I focalized also this morning that the microstructure and interfaces of course that influence the gross behavior can be detected at very different length scales.
Yeah.
So we have micro, that is strictly micro, but also meso, and meso. In meso, I want to include masonry, of course, and the mortar and the failure along mortar joints and within the elements that in this case are the bricks. I suggest to follow the whole course to have a wide overview concerning various different approaches, as I said before, using also different languages, but with the same aim and with the possibility to modulate this kind of different languages to the unique aim, that is modeling of complex materials. Yes. That can be composites and many other kinds of materials. And I would like also to say to our students that we will share all the presentations and of course the publications selected by the lecturers that are useful to for deepening all the contents of the talks. Right. Please,
if I just to add on this, Patricia is right. You know, somebody I learned, I forgot now who was that, who said all the models are wrong. So even the models, and some of them are useful. So for me, probability is one of the ways to see how useful they are. Because it used to be like a model was suggested by a very famous professor. Say, oh, it must be a good model. Today, probability shows that at the end, if you have a lousy probability distribution, you cannot really use it for this particular class of problem. So this is becoming a little bit more objective. This would be the idea. Yeah, this is I just course tested low strength mortar in master study and had my mid-plane mortar failure. Some of these old tests. I do realize interface tests. Yeah. Okay. Did you have a question? Yeah. As I said, there's no limit to complexity. You can add as much as you want. It's just limit becomes computation. Like for example, you know, physics guys, they say they can predict what happened to the universe. But I forgot now what is the number of particles in the universe. It's such a tremendous number that at the end they cannot predict because it's not computable. And that is why you start with this reduced model. And reduced models is about modeling. So then you start selecting what is essential, what is not essential. And what is essential, in principle, everything. But then you introduce something which mathematicians call quantity of interest. You have to define what is essential to you. And then you start to, and this is what we do in in these problems. For us, essentially strain energy, because whatever happens, when I explain to students at the beginning courses, basically you put this loading on the structure remains deformed, and you have a trace what happened in terms of the strain energy, basically. And for example, finite element method, for that, just one remark, is the discretization method which has the lowest approximation error in terms of the strain energy norm. No other discretization method can have such a good estimate of the strain energy. Now dissipation, you cross limit of elasticity, strain energy which is dissipated, which is lost, called plastic or damage or whatever, it's actually dissipated energy. So by the same token, finite element method produces the best approximation to the dissipated energy called plastic dissipation, damage dissipation. And so using quantity of interest, which are strain energy and plastic dissipation, for engineers, these are the best possible choices given formulation and given discretization if you use finite elements. Now, if you use something else, you might not be doing such a good job because your discretization error will be, there's something called best approximation property. I have it in my book, basically. So it's very easy to show. Any other discretization technique rather than finite element will have lousy. For example, there's fantastic work. I'm not going to be a bad mouth because this is one of my former Berkeley guys, and Berkeley guys are special mafia. They respect each other, even if they are from very different generations. One of the top products of Berkeley School is Tom Hughes. He's a great guy, very intelligent guy. And for years, he was able to build many, many things. Now, he built something called isogeometric interpolations. These are great interpolations if you know what you're talking about. It's like XM. If you know where the crack is, you put XM, you get the best result. If you have isogeometric, if you take a linear elastic geometrically non-linear problem, your isogeometric cannot do better than that, because these are the smoothest approximation of wonderful surface. And I saw Tom Hughes showing wonderful results where you have this instability of a shell, and you have this bunch of these fleas, what it's called, and captured in a wonderful way. Finite element can never dream about that. If I want to get the fracture, my displacement field is everything but smooth. There are jumps, there are discontinuities. Put something smooth on that. Fourier series will not even converge. You take discontinuous function, take Fourier series, you won't never get convergence. So you have to know mathematics, engineering, physics, and then you know what you're talking about. Of course, Tom Hughes knows that, but he's a good salesman. He's American. You know, he actually, I remember when he was doing this as a geometric, that's the reason he explained his first lecture. He said this graphic stuff, that Pixar, this guy who created Apple, I have Apple phones, so I cannot criticize. It's a wonderful product. This Steve Jobs, he also was the boss of Pixar, which produced Toy Story and these movies. And they actually use these nerves to have a wonderful images of, now they no longer employ actors like Marcello Strani. If he was still alive, he would never get a job because you can produce more beautiful Marcello from fake images, you know. And so basically, this is great for the movie. So he said it would be great for finite elements, but you lose completeness of the basis. In polynomials, if you have an analytical function, every solution in terms of the Taylor series, it could be represented in terms of polynomials. F of x minus x0 is equal to f of x0 plus x minus x0 times first derivative of x0 plus 1/2 x minus x0 squared times second derivative of x0. And you put x minus x0, x minus x0 squared, you get the linear interpolation quadratic, and you finite element can represent any analytic function. These guys cannot, but can represent much better some special things. Yes, and then you use these special things and you sell it. Why not? This is the idea. So you really have to have a really deep knowledge of physics, applications, mathematics, engineering, and stuff like that. And then, of course, you go with it. By the time you learn all this knowledge, you typically solved enough problems that you are well off in life, and you don't worry about this. But too bad. It's really, it has to be a little bit of a more important to say what we do as engineers is overall, maybe not more specialized than the other guys, but is the most complex because we have many criteria to take into account. You know, the other guys, they only worry about one thing, and that's all. You know, they always said this isogeometric for this, and they don't worry about that. Ising model is one and zero, and that's it. We have 16 phases. You know, what the hell now you do? Yeah. It's not possible. This is his dream, you know. that other people recognize that we are a solution to their problems. But you know, it's not enough to recognize, to say thank you guys, and that's all. You have to be what you call valorisé in French. They have to be paying you as much as soccer players. Pardon me? Yeah, but really, if you think of that, honestly, that we live in such a comfort, that we have airplanes that take us in 1 hour, 45 minutes to Rome, that we have cars, that we have whatever, wonderful buildings with the lights and the zoom. It's all because of engineers. It's a really big contribution. There's a... Pardon me?
About functional problem,
Yeah.
presentation problem, you answer me in the second part. But the question is this: what is the difference between the proposed method and the X-FAM?
Yeah, but maybe the best difference would be here.
Because the idea is to enrich the displacement at the jump functions.
Yeah, basically this is in a nutshell, this is XM. So basically XM is doing this. If you have a bar with the possibility of breaking here, you introduce the jump, which is supposed to be connecting the breaking, and then basically you have to describe this with some degrees of freedom. So you need shape function, which are product of this heaviside function and this jump. And this is handled by the nodal parameter alpha. And then you have another function which is handled by second nodal parameter. So XM always have extra parameters which are placed at the nodes. Where this is embedded discontinuity, it has these parameters describing the fracture which are placed inside the element. So you can say if you compare these interpolations with this one, and this one, that this one is better. That's what they said. Because it happened to be a problem where this stress field, which is constant because it's a simple bar. If you take a simple tension test on a simple bar, you only produce a constant stress in every section. There's no other way you can do it. This is called equilibrium. That doesn't depend on the material. But if material is heterogeneous, like it happened to be here, one material here, this is aggregate, one is there, cement, with 7 times bigger Young's modulus, that means the strain will be 7 times bigger in cement than in aggregate, because the same stress divided by 7 times smaller. So basically you need extra mode to repair this, and it's again embedded discontinuity mode. And once you have that, you get perfect results, and better than XM, simply because you know that this is enhancement of your total strain, and this is your plastic deformation, which is a little bit crazy. It's localized and so on and so forth. And this is really the idea. So basically, we are chasing the dissipations. They are chasing a representation of the crack. And okay, if you know where the representation of the crack is, you can run your XM. But most of the time, you don't know where the representation. We use, on the other hand, XM for the case where you have a reinforced concrete. You see, another place where I use XM is here. I actually know where this reinforcement bar is. In 4-point bending, it's actually at the bottom. So I have every line at the bottom. It has these XM representation of one slip. And it is important to have XM because XM give you no local representation. Given that you have now nodal degrees of freedom of a bond slip, I can be connecting the slip in one element with the next element with the next element. And actually I have to connect all the slips along particular reinforcement path. And it then does the most appropriate job that I want it to do. So this is like 2 illustrations. In reality, these are different approximation methods, but these are 2 illustrations what it does, basically. So it does a good job in terms of representing what it has to do. But I know where I put reinforcement bar. On the other hand, I don't know where the crack is. In fact, this idea of XFAM using for the fracture problem came from Griffiths. Griffiths put this criteria where it started with the existing crack. And then Griffiths criteria is about the existing crack. Of course, if I have a crack already, then I can use this type of fracture. But if I don't, and the goal is composite heterogeneous material, who the hell knows where's the weakest point? I don't know. So you estimates and parameters, so this parameter happen to have fracture energy. And this is the energy which is needed to completely break structure that we separate and only glue put it back together. And so that's the reality. Whereas XM really held a position in the track, which is much less reliable in composite. So hopefully, in a nutshell, these two examples illustrate what the difference is. Okay, Marco.
I don't know if there are any other questions or.
Let's see if I chat.
No?
I was just this was mortar was already asked, so go ahead with another one. There's no more question. Yeah. Yes, go ahead.
When you talk about concrete use Voronoi Cells.
Yeah.
Question is your opinion about the capability of your method using Structurale method. In this way,
Yeah.
you don't have necessary to meshing the grains or
Yeah, the way I understood the presentation of Franco Prezzi, the last time I was in Roma was in 2018. Yeah, this 2018 conference on fluids, Franco Prezzi had a whole session organized on the virtual element method. So these are elements which are built in any arbitrary shape, and basically they have a continuity of the displacement along the boundary, which is very difficult to build in any arbitrary shapes. So for the case where the continuity of the elements is a problem.
Is more computing the shape function.
Yeah, of course, shape functions are adjusted only in the interface and so on like that. I agree. But basically, it's again, this is very special technique for very special problems. As far as I know, I work on electromagnetism. So we have very crazy, I can show you that. We have a papers with a young guy who is very, very good, and we are trying to build a book on that. So book number 10, if everything is right, will be about electromagnetism. And basically, the PDF, just a second, okay. And then here's a computation mechanics. So Patricia wanted to have papers, there are many papers, man. And computation mechanics, just a second. It's a very recent paper, here it is. So Pablo Moreno, 2020, there you go. So, oops. Okay, so if I share screen. We have this one, multi-field variation mixed for electrostatic and magnetostatics. So these are kind of crazy interpolations that require the following. Here I don't know if you study electrostatics or magnetostatics, you have something called electric field. You have something called electric displacements. So if you want to compare the mechanics, electric displacement compares to stress, electric field compares to strain. Electric field comes from a voltage potential. So you can introduce the voltage potential to build this. But the operator is, this one is gradient, and you have like a curl type of operator, certain it is. This is kind of curl. So it becomes very tough to represent this with the. Yeah, no, so now these virtual elements will be perfect for constructing an interpolation of this kind. What we did is we build an element. Yeah, I can show the element which has a what you call it, electric field projected along the edge, and this is the only interpolation. Then you have an electric displacement projected on the facet, and so on and so forth. So virtual elements will be perfect. In fact, in this particular mini symposium in Rome in 2018, I think Donatella, who is the wife of Franco Prezzi, already presented stuff for electromagnetism. So basically, I mean, they already thought of that. They don't need my advice for that. So for very special problems, you have very special interpolations. Yeah. But it all depends what you study. This lecture was about electromagnetic about fraction. Next time, if Patricia invites me, we'll talk about electromagnetism. By the time, I hope we'll have a book, because my job of a chair, I have to be adjusted to this ERC. So I work now electrical engineering, mechanical engineering, civil engineering, whatever. The only thing I didn't start yet is financial engineering. I should maybe get a degree in financial engineering, then I could really complete the whole thing. Yeah. If you have a degree here, I can do that really. Yeah, that would be really good. Yeah, we have something called industrial engineering. This is like a soft layer management, really, not much science. Yeah, but when I was a student at Berkeley, I was most of my lunches. I stayed in for half a year in something called International House. This is like dormitory, very nice, building off the campus. So basically 600 students, 300 Americans, 300 foreigners. Every meal I spend in Americans to get language, and I like their mentality. Everything is great, everything's positive and stuff. So first question, you meet somebody, what is your major? What do you study? So I had to say structural engineering, civil engineering, like it was like a shame. There's like international finances, management this, management that. I said, what the hell is this, you know? Yeah, like really. So these guys are way ahead of us, you know. All the clever guys are studying something, you know. But, you know, we have to learn a little bit more to sell these things, because sometimes they're really, you know, I had really very interesting observation. I read recently this guy, Elon Musk, you know, his guy built a space X to send it to a space station, you know, and he built Tesla. You know, Tesla is producing number of cars, which is like which is in hundreds. And the value of the company is bigger than Toyota, which is #1 production of number of cars. And I know I drive Toyota for years. This is fantastic car. Elon Musk with his church, in French you say church, this is like a demagogical story, managed to build Tesla to high level. And he came to a German guy who is building these drilling devices. So he's going to build a big tunnel around Paris, so we can make a big line of metro around Paris that will speed up transportation now. So these are special drilling devices. So Elon Musk had the idea to build like a perfectly straight tunnel from Washington, DC to New York. And then they go, they send a train with 300 kilometers an hour like that. And it goes like in half an hour from New York to, and this guy said in the soil to build a perfectly straight train. And you have just a small deviation, and the train 300 kilometers would touch the layer of the tunnel, and it will pulverize. This guy's crazy. He doesn't know what the hell he's talking about. But he's a really good dreamer, you know. He's selling to the guys who have no idea what the hell he's talking about. He's big boss. He comes with billions, and the guys then after that they do it. You know, somebody knows, but you have somebody to motivate the people. So what I do with my PhD student, there was a time where I would really work a lot with my particular students. When I was a young professor, maybe 20 years ago, my colleagues were accusing me that my students did thesis on steroids, because if they were stuck, I would do coding the first one, and then they learn and they code after me. So I had no more than 3 or 4 students. Now when I have always 10 students, I can just talk. And if he or she cannot survive, it's really tough life, but they learn much more. So basically, sometimes you need this global vision, and people working with you, they have much more actually than if you do babysitting like you're 2 years old and take you from the whole story. So this is really the story. You need like this, let's say, guru motivational guys, and you really, if you have clever people around you, probably Elon Musk has the strongest is to choose the clever people. I also read one of these summer vacations when I had time, when I learned new domain and stuff like that, like physical, or whatever, mathematical physiology or whatever, electromagnetism and stuff like that. I read a like biography of Steve Jobs. Steve Jobs never knew how to code. He only learned how to have calligraphy. Wonderful. And he dropped, and this is, if you look screen of iPhone, is the most beautiful letters you can read, even small screen. So the guy found the great people, and he motivated them to do the fantastic product. And in California, you can speak in a way which is not very formal. In Europe, we have to say in French, vous, and this, you know, and then you cannot say bye, you say, je vous prie, like that. But he was saying, you know, he got a good guy, he wants to hire. He said, what you're doing is bullshit. And if the guy says, okay, of course it's bullshit, and he stopped fighting, he kicks him out. If he fights, he said, no, it's not bullshit, I do this, I do that, okay, you are hired. So